Turn this down just a smidge. Check, check, check. See if the audio level sounds good. Still sounds high. Hopefully is everybody seeing me yet? It says starting live. Hopefully we are live. It says live. Okay, whoops, I have speakers I have to turn off. Check, check. Okay, looks like I've got multiple audio levels going right now. Hopefully this is going to keep me on my toes so that I don't lose my audio. Good, everybody's saying I sound good, audio good here. And I do have my phone on today, so any VIPs who are watching who happen to have my phone number, please call or text if anything goes awry and I don't catch it. We're not going to do another 17 minutes of complete silence, which was quite amusing to watch actually last time. I can't believe you guys hung in there. What troopers you were to hang in there for so long while my audio was out. But I've got the screen up. We'll see how long my television lasts. I've got a TV I'm staring at over here. And hopefully it will keep me, you know, I guess abreast of what you guys are saying, as long as it doesn't go out. My television has a tendency to get overheat and it might turn off, so because it's a big screen TV and it gets hot. So anyway, so hopefully I've got enough things in place that will keep us on our toes for this this new course. So thank you for joining me. This is now the second, I think this is now the second one for radio bursts, for solar flares and radio bursts. And I heard a couple comments early on that said, or saw a couple comments early on that said something about how do you scream in space? Obviously this isn't an audio scream, this is a scream in radio noise. So no, you don't have acoustic waves per se in space. You do have acoustic waves in certain plasmas and on the sun, because you actually can get acoustic waves there. But no, we're talking mostly electromagnetic radiation and radio noise that then of course can be translated into screaming. And anybody who's an amateur radio operator or emergency responder, you guys all know what it sounds like when the sun screams. It drives you crazy because you can't hear your own radio signals. And so we are going to continue on this trek today with this second class. This one is going to pick up kind of where we left off. I'm going to do a little bit of a review first to kind of set the stage and remind everybody where we were. I won't spend too much time on that, but because I did have that audio dropout last time, I will pick up some of those slides that I was meaning to present last time. And then we will go, after that, we will go into flare dynamics, and I'll show you a whole other side of solar flares. This is the side that most people talk about when they talk about solar flares. They don't talk necessarily about the radio bursts. I chose to do radio bursts first because I think it had a much more relevance to everybody who, you know, has to deal with space weather on a daily basis. But now we're going to get more into, I don't want to say the scientific side of it, but it kind of is, because this is the side that a lot of scientists really, at least in space weather scientists, we really study, because we're trying to understand the physics of the sun itself and the physics of these dynamical processes and compare them with the models that we've developed. And the only way to do that is to look at the sun in a lot of different wavelengths and try to understand what is happening at each stage of the flare. So I'll go into these processes and we'll see a little bit more eye candy here. Let's see. Hello from Montana. Thanks for your teachings. Wonderful. Good to see you all. And sounds perfect. Nice graphics. Only color temp running warm. Oh yeah, you see. Yeah, hang on a sec. Let me see if I can adjust that. I probably can. Hold on. Give me a second to adjust my white balance. Let's try that one. I've got a picture of me up here, so hopefully, gosh, it's a long delay. I still haven't, gosh, that's like a 12-15 second delay for the download. Okay, I'm switching it now. Let's see when I come back on screen if it looks better. What do you guys think? Does that look better? I'm waiting to see if anyone's commenting. Hopefully that's a little bit better. It looks a little, I look a little bit more green, not quite so orange. So hopefully that will work for everyone. Okay, anyway, unless I see any much better in the color temp. Okay, cool. So we'll do that. We'll do this one and we'll run with this. Aren't you glad I knew how to fix that? Okay, so this is Scream Heard Round the World, Solar Flares and Radio Bursts Continued. And I'll stand, I forget which side I'm supposed to stand on here. I'll stand over here. These are my steering committee members on this side here and my mini course patrons. If your name isn't on the list yet, please forgive me. I have not updated this from last month, so I've got a couple people I need to put on my VIP list, and I definitely have a couple people who are mini course patrons who I haven't added yet. But thank you so much for everything. You guys are amazing. Not only do you help me steer this ship, if you're a VIP member, I have meetings with you guys once a month, and you really answer some really tough questions and give me some incredibly good advice in terms of how to make sure that I stay on task and on point when it comes to the various aspects of this community that really are clamoring for this information, and how to go about teaching it and not get lost in the academic weeds, because that's what us scientists have a tendency to do, right? We oftentimes want to teach from the point of view that we learned from, and that's the phenomena and all of this, the cool eye candy stuff. But really, it's the relevance of space weather at Earth that makes it so important. And so the VIP members really help me with that. And then all of you mini course patrons, I have to tell you, you guys are the baseline point of departure, guinea pigs for the Millersville courses, the graduate level certificate program that we're building and we're going to launch in December. So this material that you see here are forming the two main courses of that graduate program, which are the space phenomena, space weather phenomena stuff, and the effects at Earth. So those are the main two courses out of like a 5-course set. So I can't thank you enough, because all of your support is making this possible. I wouldn't be able to do it otherwise without you. And all of your comments, on YouTube and on Patreon really help me understand where these courses work and where they don't, and so I can fix them and make them even more relevant and better. So thank you very much to all of you. Okay, what happens when there's a solar minimum? Now. This is what happens when there's a solar minimum. Right now the sun is ridiculously quiet, and it's very difficult for me, honestly, during my forecast to try to find stuff that's interesting because it's just not doing anything. Yeah, it's but the only thing that is interesting is cosmic rays, because cosmic ray radiation is not being shielded out like it would normally be. So we're getting more intense cosmic rays penetrating and causing issues for flights, for people who fly a lot. And we're just beginning to learn a bit about that. We don't know all that much about it, but there's really a lot of neat research going on in that arena, because people are beginning to see that there's pockets. As you fly over different areas, the Earth's magnetic shield is it's not just consistent. It's not one shield. It's weak in places and strong in places. And as we fly over different regions, we're finding where the weaknesses and the strengths are, because we see higher flux in this area and lower flux in that area, and it's very interesting. And so hopefully eventually we'll be able to map all of that out, but it's going to take probably decades for that to happen. All right. I read a paper recently that M-class stars can really micronova. I think the definition of a micronova, there's a lot of flash and circumstance. Anything, any sun at any time can do something like that, but the probability of that happening is so low that it's really much more speculation than it is reality. So, I don't really go into that, because that's not really what we deal with every day. But is it possible? Sure. All right, let's get into it. So we are, let's see, where am I going to stand? So this is the one of the charts that I presented last time. This is when I was talking about, okay, I'll make sure I stand on the right side. This is when we were talking about how the neat thing about probing the sun with radio frequencies allow us to actually see the sun in a totally different perspective than we do in white light. And I'm just trying to review a little bit, and I'm a little bit distracted because I see my television thing right here. So if you see me be distracted at first, I kind of have to just get used to this. The first picture that you're seeing here, this is a picture of the sun in white light, and you're seeing that in the total solar irradiance. That's kind of this plot that's overlaid. You're actually seeing a drop in that in that solar irradiance, that was because of the sunspot. You can actually see that big, heavy, dark sunspot group that's going across the sun right there. That actually dropped the solar irradiance a little bit. As you can see, it's not a huge decrease, but it is a decrease. And so when we talk about sunspots and we talk about them being, where solar flares come from and why they're so noisy, but wait a minute, they're dark. How can they be, how can they increase the solar flux, or how can they cause radio noise? How can they do whatever they do if they're so dark? Last course, I went over that. I went over what sunspots are, why are they visibly dark, and also the fact that they are only dark visibly, but in other frequencies like radio noise, they're incredibly loud. And that's what this second plot shows. I'm kind of standing in front of. When you look at the sun in radio frequencies, this is from the VLA, I think I have it mislabeled. It's not 14 gigahertz, it's 1.4 gigahertz. When you look at the sun in radio noise, you actually can see those sunspots. They're radio loud. So sunspots are visibly dark, but radio loud. And that's why they cause such a problem for us here at Earth with the amateur radio operators and emergency responders, because we're dealing with the fact that these sunspots, when the sun is very, very busy, just even having the sun in the wrong place, you can hear it. The radio noise becomes so loud, even just with a bunch of active regions, these sunspots on the sun, you can get a lot of radio emission. And then of course, when you have a solar flare, it makes it even worse, right? Now you're going to actually get radio bursts. This is the quiet sun. This isn't a bursty sun. This is just what sunspots look like in radio frequencies. They're loud. They're just noisy, chirpy, chirpy, chirpy. And then when these flares occur, then you get other things. You get radio bursts. So well, I guess this isn't a flare, but you'll see that in a second. And I talked about this more. Let me stand on this side. Here is a sunspot on the limb of the sun. So as the sunspot rotates off of the sun's, onto the sun's edge, you can kind of see that dark area right there. That dark area is showing the actual sunspot. And then above it is a contour showing the contour of the radio noise source. And notice that radio noise source is not sitting on the sunspot, on the surface of the sun, but it's actually sitting above, right? And the reason for that are because of these magnetic loops. And I talked a lot about that last time, and I will talk about it again because we are going to go into the flare dynamics, and you'll see even more about why the sources of the radio noise come from these magnetic loops up into in this region. This is actually where we have a lot of activity, where there's a lot of magnetic reconfiguration. So the magnetic field on the sun, in the dynamical processes that happen on the sun, the magnetic field is critical. This is why we pay so much attention to it, even over other things. I mean, people talk about the electric universe and all this kind of stuff, and everything's, you need to look at the electric fields and electricity moving. No, not necessarily. We need to look at the static structures that the magnetic field creates, because that's how we see what the structures are and what breaks. You can't see that with electric fields. Electric fields are constantly moving and changing. They change so much, they're so varied, they're very hard to study. But magnetic fields, which are, the distant, not a distant cousin, they're really connected to electric fields. We study the magnetic fields because they're a lot more, I don't want to say stable, but they're a lot easier to study and a lot easier to understand when we're looking at processes like this than looking at electric fields. Anyway, I won't go too far into that. Moving on to, oh, that's right, I'm not going to talk about the emission processes. Moving on to typical radio emission mechanisms. I mentioned this last time. Again, this is part of that review. If I stand on this side? No, stand on this side. Okay. We have multiple types of emission mechanisms. I spent quite a bit of time last time just telling you that if you want to dive into the mathematics of each of these, the plasma radiation, cyclotron, synchrotron, thermal radiation, all of this stuff, you're going to get into a lot of mathematics very, very quickly, because it goes into plasma kinetics. And it's very, very complicated. So I'm putting this up here for your reference. These are the main forms that cause radio bursts during solar flares. And go ahead and look them up at your leisure, but also with the caveat that if you plan to look at the physics of it, it will get messy very, very quickly. And then I'll go into the standard flare model. We'll talk about this a little bit more. I spent a lot of time on this in the last course, but I just want to remind you a little bit about it. For those of you who had been to the CME course, you remember this picture quite well. We have the flare, we have this loop, this yellow loop here. Whoops, let me back up. I always have to do this on the green screen. We have this yellow loop here that is kind of trapped, it's jailed in these other magnetic field lines that are kind of jailing it. And this, as the magnetic field lines pinch in, it releases this loop and it goes outward. So that's the second picture here. So now you've got smaller magnetic field lines that have because they broke at this what we call the X line here. They break and reform, and you get smaller magnetic field lines here, and then this rope that kind of sits up on top like that, and it moves out. And in that process, or even part of that process, even if there's nothing released as this magnetic loop goes out, because as we get into flare dynamics, you'll see that you don't always have that. You don't always have a coronal mass ejection or this flux rope or this solar storm. There's lots of names for it. That isn't always released during a solar flare. But when you do, you have a lot of stuff going outward and a lot of stuff going inward. And that's what I'll do if I stand on this side now. So what we're taking a look at now is a much, let me stand over here, is a much more compact and a much more kind of a zoomed in picture of just one of those magnetic field lines. You can see that field line in blue essentially, and it's kind of pinching in, trying to make itself almost like a figure 8. And as it pinches in, okay, it's going to release stuff up and out into interplanetary space, and it's going to shoot stuff back down to the surface of the sun. And last time, again, this is just a review, but the last course I went in very great detail as to what all of these, like you see all the little black circles, those were all sources of radio noise. In this case, mostly hard X-ray, I think is what we have labeled here. But you have hard X-rays coming off of the foot points, you have hard X-rays and soft X-rays coming off of this lower loop, this red, whoops, let me go over here, this red loop here, okay? So you have microwave emission, and then as you go up to the top of this thing and you move outward, you have other types of emission that come out that are even lower in frequency, and I'll talk about that in just a sec. I think I have that plot as a review. Let's see, is the sun raining as mentioned in a paper where the plasma jumps magnetic lines, or another recent paper? The sun raining. Plasma jumping magnetic lines, we have cross-field diffusion, we have, I'm not sure what that means. Is that on the sun itself? Is that plasma rain? Sort of. I mean, that plasma rain is part of what, as a matter of fact, it's part of what I'll talk about right now in this particular chart. It's part of what causes some of these emissions that we get, especially early on in the flare. In this case, let me stand over here. In this case, what you're looking at now is a side view, and I did show this chart last time. It's a side view of the sun, and so now you're looking at the magnetic loop from the side, okay? And what you will see is that, now this, granted, this may actually be a post-flare loop, and after the end of this talk, you'll understand why I say that, because that's part of the flare dynamics that I didn't get into last time. So this picture may be cheating just a little bit, but it's illustrative, because I'm going to show how the electrons, when you get plasma when you get magnetic field that's pinching in and it's shooting something off this way and then shooting stuff down, what you actually get are are particles, let's say an electron beam, that shoots down one of the, the magnetic field lines here that are jailing this plasma. And all of this light that you see being emitted, this light is heat. It's showing you that the electron beams that are shooting down are hot, and they're being heated. They're also, because the electron beams are going into a very dense sun, there's a lot of material here, they're actually emitting what we call Bremsstrahlung radiation, and it's what we call braking radiation. It's because the electrons are going by protons, and they're bending, they're changing their direction. And as they do that, they emit X-rays, in this case. And especially when they hit to the foot points, if I point to the foot points over here, no, up, right here. right here where the arrow stops. Yeah, that right there, that is the foot point of where the electrons stop and basically hit the kind of hit the surface, if there is such a thing. And that's where you get the really hard X-ray emissions, the highest energy stuff. And I might even have yeah, you can even see that in this plot. So that's where you get the highest energy stuff. As I've mentioned before, you get the highest frequency stuff at the surface of the sun. As you move further out and we drop in density, you get lower frequency stuff being emitted. It's just the way the physics works. And here is a really good example of that. Again, on this side, you're seeing that model showing the 2 foot points from this loop that come up. These 2 foot points, if you extended them into the plane of this of the wall here, so that it's not just one magnetic loop, it's a whole long chain of them. So now you've got a tube. These foot points are no longer points, they become tracks, almost like railroad tracks. Those are the ribbons in what we call a 2-ribbon flare. And so those foot points, you have a hard X-ray emission all along those train tracks that are on the surface of the sun. You have this loop that comes up where you have soft X-ray emission, that's the SXR in that gray loop. On top of that, you get the microwave emission, slightly lower wavelength, or slightly lower frequency, I should say, slightly lower frequency. And then up higher, this is that X point. This is where you have the magnetic field pinching in and squeezing and then breaking, and then the top part lifts off, and that's the coronal mass ejection or solar storm. And then you have stuff that's shooting down. So that's why you see arrows going out this way, that's showing stuff leaving. And you have arrows going down this way, that's stuff raining back down. All this is plasma rain. And then you have other things that happen afterwards where it actually goes back up, what we call chromospheric evaporation. And I'll talk a little bit about that. So there's stuff that's going up, going down. It's really cool in all sorts of different wavelengths. Some are radio emission wavelengths, and that gives us the radio bursts. And some of them are ultraviolet, extreme ultraviolet, XUV, EUV, FUV, far ultraviolet. There's a whole range of the ultraviolet part of the radio spectrum, or the electromagnetic spectrum that we observe flares in. And that's a lot more what I'm going to talk about today. But if I flip over here, you can see a good example. I showed this again last time. This is a picture, I think in H alpha, and you can see a kind of a prominence lifting up like this. And they actually went and were able to observe all these little X's show where radio emission occurred. And you can see F is foot point, T is top, so foot point and top. And then as you notice, as the emission goes closer and closer to the top, it drops in frequency. Again, I talked about this last time, but you have to keep it in mind that as you go outward from the sun, all the emission, the radio bursts, drop in frequency. The reason for this is because density is going down. You have a lot of high density stuff, right? Really high density plasma, collisional, what we call collisional plasma in the sun, near the sun's surface. But as you go out into the corona, it becomes collisionless. Things begin to not touch each other as much, and so they're not able, the beams of electrons and particles coming out are not able to create the high frequency radiation, like they were able to, or high frequency radio noise, like they were able to closer to the sun. So you always see the X-ray stuff clear down at the bottom. So hard X-ray, soft X-ray, microwave, and then even lower emissions. And that's why all the lower emissions are associated with coronal mass ejections. As a matter of fact, and that's what I'll talk about now. All right, question as an amateur radio operator. I still have the link between solar storm and no propagation and sunspots and propagation. What's the difference between a solar storm and a sunspot? Well, it's totally different. Sunspot can actually be a source of a storm. From the point of view of the sunspot is where a lot of unstable fields are. And you could have a coronal mass ejection be launched from a sunspot. But that coronal mass ejection, which we also call a solar storm, is actually traveling in space, and it hits Earth. And when it hits Earth, there's a whole other host of processes that happen. So when you're dealing with effects from a solar flare at the sunspot region and you get radio bursts, that's one type of space weather phenomena. If you get a CME, a big solar storm that's launched from the sun and it travels to Earth, once it hits Earth's magnetic shield, there's a whole nother process that happens. And that's a different solar weather phenomenon or space weather phenomenon. So you can't equate the two, and I can see why you get confused. It's very easy to confuse them when people call solar flares and and coronal mass ejections, they all call them solar storms. I'm trying to change that because they're really not the same thing at all. And even a solar radiation storm is very different, and I haven't even gone into what those are. That's going to be a subject of a future course. That's not this yet. So hopefully that helped. But if you go back and you look at the courses on coronal mass ejections, I said CMEs and aliens. I know it's a funny title, but we actually had some fun with it because a lot of people think the CMEs coming off of the sun are actually alien spaceships fueling from the sun, and it's not what's happening. But that's a really good course to get you anchored into what a coronal mass ejection is and how they affect Earth. I think I did 3 courses on that because there's lots of different effects. And then this one is the next one, or at least these 2 are the next in the series where I'm focusing on solar flares and solar flare dynamics along with radio bursts, which is what comes from them, which is totally different from coronal mass ejections. A lot of times they happen at the same time, as you can see, as we talk about this coronal mass ejection leaving, and I will continue to talk about that a bit. But they're still very separate phenomena that are occurring. So hopefully that helps. How does the frequency of change affect the Schumann resonance? So that, again, that's a magnetic field, an Earth's magnetic shield issue. So that I'd have to talk about in a different course. That's way off topic here. But maybe we can talk about at some point. Okay, good. I'm glad. Yeah, it's so easy to get stuck in space weather because there's never been a lot of really decent explanations as to how things work and why. And a lot of scientists don't realize why people who are non-experts get stuck because we take so much for granted. And I'm trying to undo that, hopefully. I don't know if I'm helping, but was types of radio adjustment? Okay. Oh, good. You addressed the alien thing. Yes, I did. So CME and aliens, if you've not seen that, it's classic. One of our very famous scientists, Nat Gopalswamy, is also a good friend of mine. He's a leader of SCO-STEP and all sorts of other. The guy's he's one of the gurus of our field. And I remember seeing this YouTube, like I don't know how many amateur YouTubers were doing this huge thing on these globular-looking things that were tethered, because this solar cycle, this recent solar cycle in SDO, has given us some really good observations of stuff. And there was this very, very obvious case where a CME was just stuck. It just wasn't going to erupt. This X line was it just hadn't gotten to this unstable part. So this tether got really long, and it was holding it out like a balloon. And of course, in the scientific community, this was a fantastic event to study. So of course, some of the biggest names in coronal mass ejection physics went to study it, including Nat. And I saw probably 20 different YouTube videos from various people talking about how obviously this is the aliens and that's their fuel line, you know, sucking down to the sun. And I just blew it away in this course because I literally pulled up Nat's paper that had exactly the pictures that they were showing. And it showed the CME model and how the tether line and how the X line wasn't quite severed. And the whole paper goes on about it. You know, we study this stuff. These aren't alien ships, guys. This is just physics. It's just the way it happens. So anyway, so if you get a chance to look at that, it's near the end of the course, but it's a lot of fun. Okay, back to this. I'm sorry, I get distracted. You guys can get me talking on stuff very easily. So as we move further out, and I talked about this last time a little bit, what other types of radio bursts are there? There are lots of other types as we go lower, down to lower frequencies, so basically about a gigahertz and down, further down into the megahertz. There are lots of other types of radio bursts, and we just call them type 1, type 2, type 3, type 4, and type 5. There's quiet time and there's storm time. I've kind of listed them here. You can go look at them at your leisure. I'll talk a little bit more about them, but not a whole lot more. Most of these now are associated with coronal mass ejections or stuff that is moving outward. It's not so close to the sun because as we drop in frequency, we're having to move further out and further away from the sun. It's the hard X-ray and the you know, microwave emission that occurs really close to the sun. As we move further down, it's going to be due to things that are leaving the sun and accelerating away. And this is, we're getting close to where my mic dropped out last time. So you're going to finally be able to hear all this stuff that you missed, that unfortunately you missed last time. But I've highlighted type 2 and type 3 because those are the ones that are associated with coronal mass ejections, these solar storms as they move out. If you get a type 2 or a type 3 burst, you know that there's a CME coming. May not be hitting Earth, but there's one that was launched with that particular, during that particular flare. You can't always say that anytime you get a solar flare, you're going to get a type 2 or type 3 burst. Doesn't always happen. There aren't always coronal mass ejections launched with solar flares. And that's part of the solar flare myth that I'll probably get into more next time. But at any rate, these types of radio bursts, as you can see here, and I went over them last time, these are the types that we typically see out in interplanetary space as we move further away from the sun. And we're going to pay close attention to type 2 and type 3 because of what they do. Now let me stand over here. Again, I went through this last time. Actually, I might be able to stand in the middle. Hold on. I have to look at the delay here. Okay, so on this side of me, this is that same flare model that we've been talking about. And on this side of me is kind of the way the flare, the emissions look, the radio spectrums look as a solar flare happens. Now, if I start with this one, and I'll back up just a smidge so I don't overlie. I'm trying not to. Okay. So you can see frequency goes up on this scale. Sometimes these things I'll show you, they'll be inverted. So you'll see frequency is low on the top and high on the bottom. In this case, the frequency is low on the bottom, goes up. And then here's the time since the flare. Now we're just beginning to get into the idea of flare dynamics, and we'll talk about that a bit more from a different perspective. But always kind of keep this figure in mind when it comes to radio bursts and how they are associated with some of this stuff. You have your microwave at the very beginning of the flare, the onset of the flare. This is where you'll see X-ray bursts, soft X-ray, hard X-ray, microwave bursts. This is where basically the magnetic field that I show on this side is pinching in, right about there, okay, in this area, sorry, pinching in, okay. That is the explosive, that's when the flare basically happens and you get the sun screaming broadband, and I'll show you more of that too. But that's where you see it here on this microwave burst. You see also this is where you see strong type 2 emissions coming down, or type 3 emissions coming down. Then you also see type 2 going out as the flare begins to progress. Now you're 20 minutes out, and this is all here. Basically from type 2 on out, that's all happening as the big solar storm is being launched. So if I flip to this side, it's all from everything above that, what we call that X point, that where that circle is right there. Yeah, everything above it. Okay, that is where you have basically the type 3s and type 2s, and you move on out. And so all of this stuff, the type 4, all this major cloud of orange, that is all happening as the big solar storm moves closer and closer to Earth. The type 2 or type 3 storm, I can't read it right here, as well as the type 1, all of this stuff, which happens basically all the way out to Earth, that is occurring from basically the driver of this, what we call the CME is actually called the driver of a big shock wave in front of it. And that shock wave, as it goes through all the plasma kinetics there, it creates radio noise. So it's like this big, it's its own kind of a shield, and it just drives all this noise in front of it. And the microprocesses that occur, the size of this shock, I mean, because these CMEs are massive, right? By the time they get to Earth, these CMEs are as wide as 1/4 the distance from the Earth to the Sun. That's how wide they are. I mean, that's insane, right? So like Earth going through one of these solar storms is like literally a needle in a haystack, just kind of poking through a tiny, tiny fraction of this incredibly massive thing. And the shock is oftentimes as wide, if not wider, because it's got to stand out in front of this thing, just like a shock wave would for a plane going supersonic. It stands out in front of the plane, and the shock wave is much larger than the plane that's actually driving it. So it's the same kind of process. And so you can imagine this huge wall of radio noise coming at you. And that's why you get this huge cloud, what looks like a big cloud, over a very large frequency range. As I stand back, you can see the frequency range in megahertz is quite big with type 4. And even as type 2s, you can see that it kind of goes down like this. I'll talk about that, I think, maybe in the next chart. Yeah, let's get to that now. So as we talked about that radio burst drifting down, and you can see down here at the bottom, this is a type 2, for example. You can see it kind of drifting over time. It's dropping in frequency as the flare continues. Now, why does that happen? Well, if I stand back here, you can actually see why. If we see this as the yellow being the source of the solar surface, right? And that blue, the blue kind of channel, that's the channel of, let's say, the CME driving out, okay, of the beams going out. It's just this oversimplified plot. But you have an electron beam that's being shot out. Remember I told you all that material, you have some material that is being driven back to the surface of the sun, and that causes the radio emission on the surface, but then you have stuff that's driving out. Well, that stuff that's driving out, that's being given as the example in this beam, this electron beam, that red line. But as this beam drives out, remember, it's going further away from the sun, so it's dropping in density. As you drop in density, you go lower in frequency. So it actually causes that beam to start at higher frequencies near the sun, and as it drives out, it drops. And if you were to hear that sound, it would go almost like a whistler. And that's exactly what you're seeing with these type 2s. You're seeing that drop in frequency as time goes on. And that drop continues. So as you get further and further out towards Earth, you can get into kilometric radiation. Okay? So hopefully, and I went through this last time, so I'm not going to go into the details of like Langmuir waves and that type of thing. But you have a type, I guess in this one, they're using this as a type 3 burst. I'm sorry, this was a type 3, but both of them, if I go back one chart, you can see both type 3s and type 2s drop in frequency. The type 2s drop slower, and I had made a mistake. I looked at that, thought that was a type 2. It was actually a type 3. But both of them drop in frequency because both of them are driven by electron beams going outward. Okay? And they're going to drop in frequency as they go on. Now here's an example. This is one I showed last time. Here's an example of the historical way of plotting these things, where you're actually plotting the high frequency stuff down at the bottom and the low frequency stuff at the top. I hate this. So the plot is like it's flipped upside down. But the reason why I love this plot is because it shows very, very well the difference in the beams and very high resolution. So here you can see the type 3 beams going from high frequency, remember this plot's inverted, high frequency down to low frequency, and you can see the bend. See how they actually are dropping, not just dropping in frequency, but as time goes on, they're as the time goes on, they're dropping in frequency. And then if you go to type 2 beams, pointed out here, these are type 2s. You can see they're even more. They're dropping in frequency more slowly, right, over time. That's why the slope is different. But you can see really, really high resolution of those, and I just love that because of that. And then you can see all this other noise, this kilometric radiation that's just a hash of stuff. That's from this big shock wave and a lot of the thermalized stuff coming out at you. Okay, so here's the plot where I didn't get to talk about it last time. And let me break to see if there's any question that you guys have. Oh no, sorry, Franker. Are we getting heckled again? You know, people who love Ben Davidson love Ben Davidson. People who love me, but you know, we don't have to argue. I'm talking about stuff that's totally different than what he talks about. And there's really no reason for contention. Ben's is in the fringe science field. I'm in the mainstream science field. There's no reason for contention. You know, fringe science drives mainstream science to look beyond their box, but mainstream science keeps fringe science grounded and gives them the data they need to be able to do their science. And it drives me crazy that there's got to be this contention. So people, stop fighting. Just stop, okay? We help each other. That's what we're here to do. We're not here to fight. It's not that one has to be right and the other has to be wrong. We both help each other. It's a handshake kind of thing, you know, it's a synergy. So just relax. Everybody just relax and enjoy yourselves. Okay. Peter Quinn, maybe at the end you could show us the data from the Carrington event. You know what, I'll show a little bit. I actually go into the Carrington just a smidge because it's a white light flare. So I go into it just a tiny bit, and then I will set up really essentially the Carrington class events that we've seen, which I'll probably go into next course. I won't talk about them in detail in this course, but I do talk about it a little bit, so you will get a nice little, you know, taste. Okay. I watch both. It's two different things, and they complement each other. I agree. You know, just, gosh, people, chill. Okay. Good going, Frank. I love that answer. That's great. Okay. So where was I? I got lost here for a second. You guys are entertaining me. I could just sit here and go, really? just stop talking and just watch you guys. It's fun. Okay, so wait a minute. How did it scoot up? This is the plot I wanted to talk about, and that I think my mic cut out last time on me. And this was unfortunate because this was really cool. This was talking about type 2 events and how they work and how you can see that they're actually that the coronal mass ejection, it's a shock wave in front of the coronal mass ejection that's driving it. So give me a second to take a sip. Sorry if you hear me swallowing. I swallow loudly, I know. I apologize. Okay, so let me see if I can stand on this side. No, I always make that mistake. Left is right, right is left. So we were talked originally about type 3 bursts. Now type 3 bursts are the ones that occur just on the outside of that X line. Okay, I'm going to call it an X line now. I know that's a scientific name, but hopefully I've calibrated you guys enough to know that, you know, X marks where everything either shoots down on the inside of that X or on the top part of that X it shoots out, right? Either shoots down or it shoots out. And the X line, we oftentimes call that, even in science, we call that the X line. That's the point of reconnection where everything, where you know, the magic happens. I think that's what I called it last time. And where the magnetic field is reconfiguring itself and things are breaking apart. So as we're talking about type 3 bursts, we're talking about stuff that happens right just above that X line, that magic region. And then the type 2 stuff, slightly lower in frequency, is happening further out. And that means it has to happen at the top. And I'm wondering, maybe, let me go back. Sorry if this gets anybody a headache. But I need to, there it is. I should have put this plot back in, so indulge me for just a second. So when we talk about, I want to use this side. So the magic happens right, you see with that long tether, that kind of gray tether right there. Yeah, that's that tether. That's where the magic's happening. That's where the field is pulling apart. The type 3 stuff happened basically just at the top part of that, where that tether is, which is essentially the bottom of this bubble. This bubble is part of that, is that CME that's moving out. So the type 3 happens at this side. The type 2, which is lower in frequency, happens far more at the top, right? You have the higher frequency stuff happening at the bottom, that's the type 3. The higher frequency or the lower frequency stuff that's further out is going to happen at the top of this thing. So as this bubble drives outward and it drives a shock in front of it, right? This is where we're going to start seeing the type 2 emission, okay? So now let me go back to the plot, sorry. Where am I? There we go. Stay. Okay, good. So, if I get on the right side again. Okay, so what I wasn't able to show you last time was some work that Jens Palmel, I always pronounce his last name wrong, who I love. I work with him on the ISI team, and he's wonderful. And he has a really, in this paper that they did in 2012, they did a really great figure that I thought was just extremely well done. And what they're looking at through time, you're looking at 3 different frequencies of light. So you should recognize the SDO, AIA, images. You're looking at 131 angstroms, that's in the blue. You're looking at 211 angstroms in the purple, and then 193? Yeah, it's 193 in the bronze. And what you're seeing is time goes down, and you're seeing these EUV, these ultraviolet emissions, and you can see the light, you can see the structure as you look at each panel. You can see that CME, the loop. Remember we're talking about the loop, the bubble of that loop moving outward. Oops, and I'm blocking the image. Let me back up a little bit. So you can see it over time as it begins to erupt. Why does it do that to me? I didn't touch anything. Let me hit pause. Maybe it's on a timer? No clue. So you see that loop moving outward, right? And it go down further and down further and down further. And you can see it almost leaving at the bottom, at the very last image down here. You can see that it's almost completely left the field of view, right? So that's the initial part of this solar storm, the CME erupting and leaving. Now, you also see that little green contour, okay? That green contour is 400, so it's half a gigahertz almost, 432 megahertz. And you see that green contour in front of the top part of that loop. I keep going over the image. There you go. So you don't see it in the first 2 frames, but they do recognize the source in the 3rd frame. Okay, right here. Yeah. And in that 3rd frame, okay, that's really kind of where we think the shock is really forming. You know, the eruption is happening fast enough and it's building up enough speed that it's gone supersonic. So now a shock wave has developed, and now we're getting radio noise. But notice, as it goes further out, as you go down the panels, notice that radio, that contour, the green contour that's showing the source of that radio noise at 432 megahertz. It's moving further out, away from the front edge of the bright light of the EUV image. 131, you see it again in 211. See how it's moving further and further away from the source? If you go to in 211 right here, this image, this panel, if I back my hand away, you see that radio source is right at the tip edge of that loop coming out, right? But as you go further down in time, it's moving further away. And again, you see the same thing in 193 angstroms. So 3 separate wavelengths, and you're seeing the same thing, that radio noise is starting right at the tip of that loop. But then as that loop begins to expand out and pick up speed, that radio source is moving further and further away. That is classic shock dynamics. I mean, even in the atmosphere of Earth, if you're driving you're driving a plane through, I keep using this example, but you're driving a plane through the air and you go to supersonic speeds. The faster you go, the further out in front that shock has got to stand off. So you're what we call literally the standoff distance between the driver, the plane of this shock wave, and the shock itself. The faster you go, the further the standoff distance. So as this driver, this coronal mass ejection driver, accelerates and starts moving faster and faster and faster, that shock wave has to move further and further and further away. And so does the radio noise. And that solved a really big problem. I mean, it may seem kind of simple and stupid, you know, like, oh, okay, big deal, okay, whatever. But believe it or not, for us scientists, for the longest time, we didn't know. Was it the top of the CME or was it the shock? Where was the radio noise coming from? And it took us quite a while until we had really detailed images like with SDO to be able to definitively say, okay, yes, we now can tell it's coming from the shock. That radio noise is all from the shock, which then opens up a whole new world of things for us because it means, well, wait a minute. If that shock is driving the radio noise so close to Earth, then that means as long as that shock is out there, it's going to continue to drive the radio noise all the way to Earth and possibly beyond. And that's exactly what we end up seeing. So this is one of the coolest plots from last time that I didn't get a chance to present. Let's see where I can stand. Let me stand. Do I stand this side? No, let me stand on this side. Okay. So what you're looking at here, if I can get myself almost completely out of the view here. What you're looking at is a plot in time with radio frequency going from low radio frequency to high radio frequency. So you can see, what is it sitting at? 20? Yeah, 20 megahertz up to gigahertz, right? 2-3 gigahertz. Oh no, that's kilohertz. So my fault. So kilohertz. So 20 kilohertz all the way up to several megahertz. So we're looking at the bottom end of the spectrum, but nonetheless, it shows you, it's showing you some really interesting physics that's going on. And basically, where you're seeing that initial drop, that initial heavy red line, that's the initial part of the flare, right? That was an X1 flare, okay? And that flare then launched a coronal mass ejection. And as that, remember, so you got all that hard X-ray emission and stuff like that that's not being shown. That's up at the top. That's way out of the range of this plot. But as you drive that coronal mass ejection towards Earth, now you're going to start seeing emissions that are getting lower and lower in frequency. And so that's where this bottom part of the plot becomes more important. So you see the tail end of that initial flare, and then you get I guess this is showing the type 2 radio emission. You're getting another blotch here, but this is over time. And this is over now hours. So now we're talking about not just, if you remember the other plot that I showed you that had the type 1 or type 3, type 4, storm time stuff, and it showed it was a timeline. It only showed maybe 2 hours after the flare, maybe 3 or 4 hours at most after the flare. May not even have been that long. Now we're looking at days. Okay? So if it takes a coronal mass ejection anywhere between 2 and 5 days to get to Earth, well, let me not call 5 days. A CME that's moving that slow isn't driving a shock, so most likely it's not going to be having any radio noise. But let's say anywhere between 2 and 3, maybe 3 days. Those are going to be driving shocks because they're moving much faster than the ambient solar wind typically. So they will be driving shock waves in front of them, and they will have some level of radio noise in front of them. And yes, this stuff can cause problems for amateurs, radio amateurs. Sometimes for satellites, not all that much because most of the time those frequencies are in the gigahertz range, so it's not nearly so bad. But it can cause issues, and we've seen it happen before. So, and we definitely can hear it with instruments, with scientific instruments. You see it right, you're seeing the evidence right here. So here's the type 2 radio emission. You're seeing a little bit. A type 3 burst first, then the type 2, and another, I think it continues out further. Yeah, you're seeing more and more radio bursts at the low end of the frequency range. Now, guess what? Here is when the CME, this big solar storm, reaches our upstream monitors. It says CME shock at wind. That's when, oops, come on, Tam. Right there, okay? CME shock at wind. See that? You go straight up. That's actually some radio noise as the CME is passing over the instrument itself. Then we actually get the shock arrival at Earth, and we get the quasi-thermal noise. And if I flip over to the other side, we actually get all of this hash. Look at this. You know what this is? This is Earth's magnetic shield responding to it. There's so much stuff that goes on during a solar storm. Once that CME hits Earth's shield, we've got radiation belts, we've got wave processes, we've got energization. Just like there is at the sun, we have electron beams. We have electron beams that go down into the northern and southern poles. That's what causes the aurora. You get radio noise with that. You get dawn chorus, you get whistlers, or not whistlers, you get dawn chorus, you get AKR, you get all sorts of very interesting ion cyclotron waves, all sorts of different types of emissions that then are picked up. And they're all over the frequency spectrum, as you can see. Low frequency spectrum, but nonetheless, it's there. So if you wanted to actually look at a coronal mass ejection's effects, I mean, I need to stand completely out of the frame here. If you wanted to look at a coronal mass ejection's effects, look at this from sun to mud. There's stuff. There's a lot of stuff. So amateur radio operators, emergency responders, anybody who's going to be working in space, we have to contend with this stuff. And now we're talking about colonizing the moon, lunar colonies. This noise is going to be out there, and you're going to be bathed in it. And there's going to be issues that we're going to end up seeing as we continue to work in space, especially near Earth space, because that's what we're dealing with here. As we work in near Earth space, actually that's what we're dealing with here. Once you see that interplanetary shock, everything from there on in is the near Earth space environment. This is inside Earth's magnetic shield. This is causing all of the issues that we could have. So we're going to see all sorts of strange stuff that we may not have had to deal with before as we get humans working in space more and more often, doing all sorts of things, repairing satellites, who knows, zipping back and forth from Earth to the moon, lunar colonies on the South Pole. I mean, you know, Toyota's jumping into the fray with their little rovers. If you're a Patreon member, I'm going to show you, I'm going to do a behind-the-scenes video. I basically have it done. I just have to polish it up, and you're going to see like a 3-minute video where I go into the details of some of this stuff. And we have so much to contend with that we don't fully understand yet, that even scientists are still trying to understand the whole mechanisms that drive all this. And we really don't know how it's going to interfere with all the, you know, just the things we take for granted when it comes to communications and even just how our electronics function. So, you know, space isn't space. It's not quiet. There's just a lot going on. And so this kind of sets the stage for what I'm going to talk about, or how I'm going to segue into the next aspect of flare dynamics, which is talking more about the light emissions, the EUV, and the different stages of flares and why they do what they do, and how we are testing our flare models with some of the observations. So let me just see, did they check for space weather for the Apollo missions? You know, they didn't know that much back then, and they got lucky. And there's been a lot of forensics done, and the funny thing is, and you can look this up, I mean, it's open access. If any of because there were solar events, there were radiation storms especially that happened during the Apollo missions, but none of them happened when these guys were out on the surface of the moon or in flight or anything like that. But if they had, there were a couple really big events, and if the astronauts had been exposed at that time, like walking around on the surface of the moon, they would have gotten lethal doses of radiation. And that's well known now. So, you know, there's a lot of people who are cavalierly talking about, you know, oh, we're going to have people back on the sun by 2024, back on the moon by 2024. And, you know, anybody who follows this channel knows that 2024 is when the peak of the next solar cycle is supposed to be. Is that cavalier, you think? Maybe? Just a smidge? Don't get me started. Don't get me started. Okay, yeah, let's take a trip to the sun at night. I'm with you on that one. We'll be sure we'll land on the dark side of the sun. How's that? Okay. But actually the reaction from Earth's magnetic field is interference with the pressure. It's not a magnetic field, and I have no idea what you're saying. The moon passes through the Earth's magnetic tail very frequently. So yes, it's inside the Earth's magnetosphere. Not all the time, not when it's on the sides, but as it passes through the Earth's magnetic tail lasts 130 Earth radii plus out. So yes, it's dealing with that. And we may even see issues with plasmoids going over the moon, because how the Earth's magnetic shield deals with solar storms is that it ejects junk down the tail. And we don't really have any long-term measurements knowing how, let's say, a human colony would even deal with that if it got hit by a big plasmoid going downhill. Maybe nothing. I don't know. I'm not a magnetospheric physicist. I don't know the details that well. I just know that there's a lot of dynamical processes that we've not really thought about in terms of lunar colonies, because most of the people in my field, they don't even talk about humans. They don't care. They're trying to understand the physics, right? So they want to know the basic fundamentals, and they look at the human spaceflight as kind of a distraction from the real science. So you don't see a lot of that pulled together, not at the level that it needs to be if we plan to be, you know, doing more than just dabbling and passing through. We plan to land and stay on the moon. Here's an example. I'm sorry to digress, but I'll just mention it. We found out from there's an instrument on the Lunar Reconnaissance Orbiter. It's an instrument called Crater, and they flew some TEP. I think it's TEP. It's kind of like a Teflon, and they flew this material because it kind of simulates the same kind of stuff as human skin. And they got dose underneath it. They measured the dose underneath it, and they found out that the lunar surface has an insane neutron albedo, at least on the sunlit side. So what that means is that the sun, as it hits the lunar dust, is liberating neutrons. Neutrons you can't stop. Neutrons, you can't shield against them. They go through everything. And so we don't really know long-term human colonies on the moon, how that's going to affect humans. But that was something that one of my colleagues at Aerospace discovered. And he's a nuclear physicist. I mean, back in the day, before space physics was even a thing, there was no space physics discipline. So everybody hired to understand what the space race was. And as soon as we realized that space was radioactive with Sputnik and all that, and that there were radiation belts, everybody hired nuclear physicists. So one of my good colleagues, Bern Blake, is basically one of the, another guru of the field. He is one of the holdovers from the very earliest days of space physics, when all of the physicists were all nuclear. They didn't even have they didn't even understand the discipline of space. It was a whole brave new, wild frontier. But he's forgotten more about radioactive and radioactivity and how it affects in materials and all sorts of other things than I've ever learned. But he found that very interesting, that there's this measurable neutron albedo, and the idea that it's very difficult to shield neutrons, and how are astronauts going to deal with that. Have you ever heard anybody talk about that? Elon, NASA, anyone? We got a lot to learn. A long way to go. Anyway, okay, enough of that sidetrack. Anybody who watches these courses, you always get me on these little sidelines that are these tidbits. You got to dig for them, but sometimes you can get really good ones out of me. Okay, Tamitha, you seem a little flustered today. Yeah, I don't know, maybe so. Yeah, I spent all night last night with my husband at his theater streaming live comedy, so I didn't get enough sleep. Maybe that's why. Anyway, okay. So what I wanted to do is kind of segue into the next part of this course, which is getting into the flare dynamics from a different point of view. Not so much radio bursts now. We're going to go more into the pretty pictures, the EUV side, so you understand a little bit more of the phenomenology and why there are so many different stages and how they happen, and how we're testing our models as scientists to understand whether or not we have the picture correct. Because it's very difficult to understand the picture of solar flares without being able to test against observations. So what this plot shows, if I can stand on the right, let me stand on this side. So what you're looking at here is radio noise from the Owens Valley radio astronomy array. And I don't remember what frequency of radio noise this is. It may be as high as 18 gigahertz or maybe as low as 1, but most likely it's high. Why? Because they're imaging at the surface of the sun. They're not imaging a coronal mass ejection coming out. So you can err on the side of higher as opposed to lower, now that you know how it all works, right? And then if I back up even more, on the other side, you can see the H alpha image of a flare occurring, and you can see the two ribbons right there, and there's some extra hash on either sides, but you can see the two main ribbons coming out. So you can see that radio noise, and you can see the image of the H alpha. And then down here on this plot here, if I can back up even more, they've got both of them. They've got okay, so it's soft X-ray image. I'm sorry, I thought it was H alpha. It's soft X-ray image. I thought it looked more like soft X-ray. Wonder why it's labeled. Oh, okay. So they're showing an H alpha image, all right, but they've got soft X-ray down here. Okay, got it. And what you're seeing, so the reason why I like this plot was because they show both the radio noise and then also a soft X-ray at the same time. So you can see over time, as the flare evolves, how it looks, how they compare. And you'll notice right away the yellow line showing the radio noise. That radio really is a burst. Pop, right? And it doesn't last all that long. Just, 5-10 minutes, maybe 20 minutes, at least at this frequency. Okay, now there's a lot of other radio noise at different frequencies. So amateur radio operators who go, oh, well, wait a minute, we can get radio bursts that last for hours upon hours. Yes, you're right, but the frequency is always changing. But some of these really high frequencies don't necessarily last for all that long. However, they last long enough to disrupt satellite phones, GPS, all sorts of satellite communications in general. It's definitely a big enough issue for any type of satellite communications that we do. Now, if you look at the green line, you notice the soft X-ray lasts much longer, right? You actually, in this case, there was probably a coronal mass ejection being launched because of all of the soft X-ray emission that lasts for a reasonably long time. I mean, you're seeing here's half an hour and it's still going. I mean, it's finally coming down. And so what this does is it shows you that really what a flare looks like really depends very much on the frequency of light or the frequency of emission in the electromagnetic spectrum that you're looking at. And so when I flip over in a moment, when I flip over to looking at flare dynamics from the point of view of ultraviolet light, whether it's EUV, extreme ultraviolet, XUV, FUV, far ultraviolet, you'll see the flare dynamics is a bit different than it was in radio noise. But I will show a couple plots that kind of overlay the two. And this is where a lot of the science is happening, at least in space weather. You're seeing a lot of, we're trying to understand how the physics of the magnetic fields are connecting, how plasma tubes are being refilled, how the CME is launching, what the role of the shock is, all of this kind of stuff. We're trying to understand the physics of that, and that's what we're going to get into, at least, topically, we're going to get into that. But before I go, I just wanted to let you know, people always ask me, well, okay, you can give me this idea of radio bursts, but what does it really affect? And so I've got two plots here. One that is, if I flip over to this side, one that's labeling some of the frequency ranges of what we see, and just some of the names for those who are not familiar with it. You've got very low frequency called VLF, low frequency LF, medium frequency, high frequency, then very high frequency, so VHF, UHF, typically TV, and then and wireless communications. And then you get into super high frequency and extremely high frequency. You can see the ranges of both frequencies and wavelengths. Okay, so if you need to, at some point, this is a good reference for you if you need to freeze this frame or take a snap of it and carry it with you during the rest of this course or even in the prior course. It's a good reference, just kind of handy to have. So hopefully that helps for those who have asked me about that specific thing. And then on this side, what I've done is I've pulled out a really nice graphic that shows kind of some of the equipment, some of the terrestrial issues that we have using these different frequencies, or that use these different frequencies, and therefore when we get radio noise from the sun, what types of things are affected. Now I'm not going to go into it because it looks like, at least as I'm looking on my TV, I can see. You can read it. I mean, you may not be able to read the frequency range, but you have that on this other plot. But you can see maritime radio navigation, AM radio, aviation radio for medium frequency, amateur radio, aviation, weather broadcasts, FM radio and television. Then you get mobile and wireless, like I was talking about, and then you get satellite and astronomy, and then 5G. So yes, and that's something I wanted to mention is 5G. Remember the 5G networks? We're about to enter a whole new world when it comes to this stuff, because with these cell phones going to 5G, the chances of space weather becoming a bigger problem, at least in the areas that need 5G to make it work, we're going to start running into more problems. So, we'll see. Whoops, speaking of, my phone is buzzing. So it's going to be a brave new world when it comes to some of this stuff. And just realize that solar flares and radio bursts do make a difference. And so when I get these questions, well, why do you care about solar flares? I mean, they don't do anything, we never have a problem with them. Yeah, we do. We actually do. And the more we rely on these wireless networks and the more we go to frequencies that are more susceptible for wireless networks, and I'm not talking about the Wi-Fi in your home. That's not a problem. But when we start getting into really, very open dayside services where they can be taken out by a broadband, a very broadband radio burst. That stuff is susceptible, and there's really no other way around it. And we're just going to start seeing that more and more often as people continue to become more complacent about what the sun can do, simply because the sun has been pretty quiet recently. We're not going to be always this quiet. So, okay. I remember a time when 5G meant enough for a new car. That's classic. I love it. Okay, thank you for mentioning 5G. We'll be very sad to see if the alarmists are correct. There's a lot of people who are very worried about 5G from a health perspective, and those people who are electromagnetically sensitive. And there is a larger there's a larger group of people than I realized, because of how many people actually reach out to me about it. And I keep saying this, I will eventually have a database of research that's being done on different aspects of at least space weather related and electromagnetically sensitive, sensitivities related to space weather. I'll have a resource of, let's say, research papers and studies that have been done. Not that I'm going to draw any conclusions from them, but at least we'll have a resource and a database up for people who can go then and arm themselves with information and hopefully make decent decisions about what, whether that's something they need to pursue with their own medical experts or not. But I will do my best to try to clear away a lot of the riffraff and the stuff that's just not done rigorously and not credible, and then also associate it with, okay, well, this has to do with the solar cycle, or this has to do with geomagnetic storms, and try to separate it into different categories so people can kind of begin to understand how maybe different space weather related phenomena might be causing issues for them if they happen to be in that very small category of people who are very susceptible to geomagnetic disturbances. I mean, we know animals are. There's issues with migratory animals losing their way. I mean, even Space Weather Prediction Center talks about that. And so there are issues that we just don't fully understand about ourselves. And I know there are people that also can't handle, like, MRIs and things like that, and people with heavy metal poisoning, people who have plates in their bodies. These things all conduct, they get currents in them, and that can cause, malaise and all sorts of things, headaches, all sorts of other stuff. Things we just don't understand all that well. So I don't ever rule all that out, and I'm just trying to help people understand that better and try to give them as much help as they can, because it's a really difficult field to deal with. So anyway, so that's what all this is for. Please use it as a reference, and hopefully this helps anchor those who are not as familiar as, let's say, amateur radio operators are, or satellite operators are, with the different frequencies and what they affect here on our planet. Okay, now that's pretty much where I was at the end of the course last time. I do still have some planetary stuff I haven't gone through, but I'll deal with that, because there are things like Jovian emission. There's all sorts of radio noise that planets emit and their systems emit, and I will eventually go into that, but I'll probably save that for the next course, because I want to get through the last few slides I have on flare dynamics. So this was what I will talk about. This was kind of where we were at, where I ended the last course. I will only get through the flare dynamics essentially the first two bullets here, because I'm going to save the solar flare myth and the Hyder flare for our next course, because it's actually going to dovetail nicely into some of the effects that I will talk about when I go into detail on our third course, which will show these events, at least these events, maybe a few more, it all depends. But I will go into the effects of big solar flares and the radio emission and the issues that they've caused for us in the past, including a large-scale GPS disruption that a lot of people don't remember, because back in 2006, I don't even know if we had smartphones yet. So GPS was a big deal for a lot of people, but not for the general populace back then. But again, I'll save that for next time. So, anybody have any questions right now? Okay, thanks, Jerry. I see one of my VIPs is helping people understand about the CME, some of the stuff I covered in the CME course. That's good. Tamitha, get your extra class license. I know. I'm not even going to get on the bands until the sun wakes up a little bit, because it's going to be too hard for me. I'm not very good at amateur radio, let alone solar minimum amateur radio. But yes, I do need to get my extra class, I agree. Will this chat be available on replay? Yes, it will. You have to give it a little time, because my courses are always so dang long that it takes a while for YouTube to kind of collate it all and get it set up. But yes, it will be. So give it some time, and the chat will be available. Oh, geez, I know. Starlink. Boy. You know, Starlink is going to have a huge issue. They don't even realize that, and some of it I'll talk about here with radio bursts, or with really the solar flare dynamics. The atmosphere for low Earth orbit, the atmosphere actually puffs out during geomagnetic storms and during solar flares. And with Starlink having such huge solar panels on it, it makes them like kites. It makes these solar panels are big, like big drag anchors, like big parachute, parachutes behind a dragster. And when that atmosphere puffs out, the drag on those solar panels is going to be so dramatic that it'll change the orbit of these satellites. So I wouldn't be surprised if we have one big geomagnetic storm, a really big one, for example, and it takes out a quarter, if not more, of the Starlink constellation in one swoop. And that's when Elon Musk is going to wake up and realize, geez, this is harder than I ever imagined it would be. Space is hard. One of my good colleagues always reminds me, he says, space is hard. If it were easy, anybody'd do it. So we'll see. But I think Starlink it's a beautiful idea, but I think, once again, I keep using the word cavalier. And I think that's because that's why a lot of commercial industry, that's the way they approach space. They want to be the first to do it and put their flag in the sand. But by doing that, they just kind of poo-poo all this stuff that really is a lot harder than they think it is. Anyway, so don't get me started on Starlink. Okay, hope you'll give a presentation at Hamvention 2020. I was there this year, so I won't be back most likely for 2 years. So probably won't be 2020, it'll be 2021 most likely. And what is going to happen with 5G? I predict increased problems with medical devices. Yes. Yeah, a lot of people are predicting increased issues with medical devices. And we're having increased issues with medical devices like ICDs right now because cosmic ray penetration is so bad. People are having ICDs upset. They're actually soft resetting. Anyone who doesn't know what an ICD is, that's a pacemaker. How'd you like to go on an airplane flight and have your pacemaker reset? No. But there are industries, people in the medical field now who are making hardware in the electronics to go into pacemakers. They're beginning to make them radiation hard for that reason. And I know of this because I've talked to some people who specifically have been pinged for their radiation hard devices. And they were very confused why a medical company would ask for radiation hard materials until they talked to me and they said, oh, I just put it together, I get it now. Now I understand why they're doing it. I'm like, yeah, it's the cosmic rays and it's these polar routes that we're flying now. And they're realizing that, people could die. Yeah. Again, cavalier. Have I said that too many times? I don't think I can say it enough. Okay. Okay, bye, Carolina Sky Astronomy. Please catch the rest of it on a replay. I know, and I'll get back to doing this now. Okay, so emission varies during solar flare evolution. Yes, so now what we're going to talk about is, I'm going to stand over on this side, is flare dynamics from a slightly different point of view. We are looking at, this is a very old plot, and I even showed, I think, part of it earlier or in the last course, but it's kind of cleaned up a little bit. I borrowed this from Chamberlain's talk that he did back in 2007 because he had a lot of really good review materials in here. So you will see his credit quite a few times. So this is an old plot, and it's talking about basically what's being called radiation flux, and then frequency up here. We're talking about radio emissions. And what you're looking at is a lot of different emission lines over time. And you can see there, I think these are minutes, and it's only going to what, 30 minutes, I think? Yeah, 30 minutes at the beginning of the flare. But you're seeing all these different lines looking very different, right? You can see me down at the bottom, you see precursor, impulsive phase, main, main phase, or also called the gradual phase, and in some cases as you get further out, it's even called the late phase. We'll talk a little bit about that. And you can see with each line, and I'm standing over this now, so I'll try to back away. Can I get far enough out? I don't know. You can see each line is labeled. Hard X-rays, okay, soft X-rays, or X-rays and the soft X-rays. Broadband EUV, this is getting into the SDO AIA wavelengths. Then H-alpha, you can catch those with H-alpha filters on telescopes on the ground. And then we're getting into radio emission. So you're seeing microwave radio emission, and then that box over here, that little black box. I'll go over here. That little black box right there. That is just showing a broadband radio emission, reasonably low frequency, 100 to 500 megahertz, just broadband emission, is what he's calling it there, during what we call the impulsive phase, right? That's when we talked about the magic happening and everything happening. We spent a whole lot of time on what we call the impulsive phase of the flare. So that's when a lot of the radio bursts that we care about happen, okay? And that's where the high frequency stuff happens. That's when you get the stuff that kills the satellites, kills satellite phone, kills, I'm just talking about reception, kills the reception of GPS, kills the transmission and reception of I don't want to say transmission, but just disguises the transmission and reception of amateur radio and emergency response. That's all happening during the impulsive phase. Okay, and you can imagine the precursor phase, well, that's when we can tell that a flare is about to happen, but it hasn't happened yet. But we see the buildup. You can actually see some of that stuff begin to rise prior to it in the precursor. But the impulsive phase is what we focused on thus far, and now we're going to focus on everything else. So we're going to talk about the impulsive phase, we're going to talk about the main phase, and what is happening during the flare, during all of these phases, mostly in EUV now. So this broadband EUV, we'll be talking about that. But we'll talk a little bit about total solar radiance, because I actually got some questions on that. But in order to talk about this, really how we want to organize things is that we kind of want to know, especially as physicists, what we want to know really is how is this affected by where it is in the solar atmosphere. So, whoops, pardon me, I'm on the wrong side. So when I look at this plot here, okay, you're seeing, and I'm going to talk a little bit about what this plot is, but hopefully this will help guide you and give you kind of like a, I don't know, a background understanding of really some of the things that are fundamental, and that we have to keep in mind when we look at these solar flares. So this is a plot that goes up in temperature, okay, and it also goes up in altitude. Okay, and what you see, the colored zones are really what we've called the different zones of the sun, where different processes are happening. So we have the convection zone that's considered below the surface of the sun. The surface of the sun is called the photosphere. That's in gray, and that's also where you see altitude go to 0 in this relative scale. Above the photosphere, we see the chromosphere. That's in purple or blue. And then you have this transition region, this little thin pink transition region. That's where a lot of really cool stuff happens. The chromosphere to transition region to corona, that's where we get all the CMEs, that's where we get all the flares, that's where we get all that really cool stuff happening, the magic happening with the reconnection and everything else. And then in the corona, it's green. Okay, now what you also see, you saw temperature at the bottom, at the top on this running up here, you see density. And the reason why these two labels are on here is because we have two different lines. We have a black line that goes from the bottom, let's see if I can get to it, right there. That black line goes all the way up, and then as it jumps to the corona, it jumps way high and up. That's the temperature. And one of the biggest questions we still have in physics, and we probably, who knows, if there's going to be a Nobel Prize in space weather, it might be the unambiguous solving of this problem, is why is the corona, the sun's atmosphere, so much hotter than any other part of the sun? There's some unbelievable heating going on here, and we don't fully understand it yet. We're getting there, but we don't fully understand it. So that's one thing. And then the other plot shows a dash line. Let me go over here. This is density. Okay, so this is what we were talking about with frequency when we talk about radio noise. Now you finally get to see a plot of the density. So it's low, low, low in the corona. As you go into the transition region, it moves a little bit higher. Whoops, not too high. And then it slowly continues to ramp up through the chromosphere. Once you get to the photosphere, it's pretty high. So it's a very high density in the photosphere. This is the reason why radio noise is so high frequency down at the surface of the sun, and why it's so low frequency as you get out into the corona. That's the density that we're talking about changing. But what is neat about looking at these different emissions, because of the different temperatures and the different densities, it means it excites different lines, different spectral lines. And here is what is really cool. This is the spectrum information, or the spectral information, and you're looking at a radiance going up, so brightness in a sense, and then you're looking at wavelength. Okay? And we've got the XUV, EUV, and FUV areas. You know, it's all ultraviolet, but it goes from way extreme all the way down to far ultraviolet, you know, right before we get into visible. All of these wavelengths are covered with all these different spectral lines. And you can see there's a lot that are green in the corona. Whoops. Pardon me. No, I'm not chatting on Messenger with somebody in the Middle East. Thank you, but no. He'll probably call again. I've got to get off Messenger. It's just too distracting. Excuse me, I'm giving a class right now. Anyway, so if you see the green, all the green, those are spectral lines that we see typically in the corona. Okay, you see a lot of iron, some magnesium, what else do we see? Silicon. I don't have them all memorized. So it's not totally my discipline. Solar physics isn't my discipline, so I don't have all of that memorized. But then you see in the red, that's a transition region. Look at all of these different emission lines. We can pick any one of those emission lines to look at and image the whole sun with. And what that means is that we get to image the transition region alone. Or we get to image the corona alone. Or look at the blue. There's some blue. There's some silicon. There's some carbon, oxygen lines. We can image the chromosphere alone. And so we get to begin to take out, just see what's happening in that layer, you know, peeling the sun like an onion, and just see what's happening in that layer alone. And the reason why that's so important is because, as you remember that flare model, as things go up, you know, in altitude, you have a lot of dynamics that are happening. You've got the magic line with the X line that's happening. You've got stuff shooting out. You've got stuff raining back down. We need to be able to know what's going on without actually standing with spacecraft right there in the solar, you know, above the solar surface. We need to, from a distance, be able to image all of these different layers independently and know for a fact that that's what we're looking at and not seeing anything else. And this is how we do it. And it's so critical when it comes to the flare model, because otherwise, how are we going to see this? How are we going to be able to tell what we're looking at when we look at, you know, this here we go, here's the flare loops, right? The 2 foot points down there show the train, what will be the train tracks, which are the flare ribbons on the surface of the sun. You've got that loop, that gray, whoops, let me pull over here, the gray loop, right? Where you have the soft X-ray emission, the hard X-ray emission down at the foot points, the microwave emission that's happening at the top where this dark oval is, and then all of the stuff that goes as it goes out above that X line, all that stuff that goes out, all this is up in atmosphere. And we have to be able to image that stuff. So what's cool is that, let's see what side I can stand on now. I'm going to stand over here. Maybe I can stand in the middle. I don't know, maybe. How am I going to do this? Let me just stand over the image. Sorry. So when we look at the model that we have right now, we basically say that X line that I was talking about, that X line, that what we call reconnection, can occur after this whole thing with a bubble up top becomes unstable. And oftentimes that's when the tether grows and it becomes really kind of too long, and there's just too much force trying to rip this thing off, and this stuff wants to fall back down, this stuff wants to shoot out, and we call that instability. And the instability then will shoot material, accelerate material down to the bottom of the loop, create the X-ray emission at the foot points, and cause X-ray, soft X-ray, hard X-ray, and microwave emission, typically right about at that X line at the top of that loop. And that's all happening in the transition region. And I've color-coded the words. You can see that transition region, that's kind of that pinkish red region I was telling you about before, that really thin region, and in the chromosphere, which was the blue from the prior plot. And we call this, when all that's happening, we call that the impulsive phase. That's when you're getting all of that hard X-ray, soft X-ray, where the magic is happening, everything's breaking, materials shooting down, all of this stuff all at once. And that happens really fast. And that's when you get the strongest radio bursts with the highest frequencies. Okay? Typically, we don't get anything happening in the corona at that time. Okay, and that's, the corona was labeled green, so I've labeled it green. Okay, because the corona is too low density and we're not really seeing the CME being launched out yet. It's not launched far enough. It's all happening in the transition region and in the chromosphere. Okay, and we know this because of observations that we've seen. And I'll show you that. And then the energy that's deposited during that impulsive phase, oftentimes as that stuff rains down, it heats plasma down at the photosphere, at the surface of the sun. And believe it or not, it causes material to evaporate. You know, it's a gas, right? It's a charged gas, but it's still a gas, so it still has a lot of the same properties a gas does. And so the stuff, material rises up back into those loops. So as I go back over here, and I talk about that gray loop, you get stuff that kind of comes back up. So you have stuff raining down first and then stuff that comes back up, and that refills the loop. Okay, after the CME is beginning to leave, the loop begins to heat up, and you'll actually see that. That's what part of the long duration, or the long duration flares, the gradual phase. I mean, you'll see a lot of the names for it. In this case, I think I'm calling it gradual phase. If I go back over here, I say energy deposited in the impulsive phase, it heats the plasma, and through chromospheric evaporation, all this happens in the chromosphere and in the corona. And yes, this is where we call the gradual phase, because some of these loops actually expand out. So this loop here actually gets bigger and expands out a little bit. And then the rest of it, of course, leaves. And what we oftentimes call these are post-eruptive arcades. And so we'll see that a little bit. This is just a plot to remind you that yes, we can do this. With SDO, we have not only ability to look at the magnetic field, which is that black and white thing right there through HMI, but we also have all of the EUV stuff, all of this spectrum, 304 angstroms. These are iron lines. We have 171, 193. These are all different emission lines that we image the full sun with. And so we're seeing different regions, like the 304 right there, that is the chromosphere, right? But as we get into 131, we're getting into the corona, this blue sun here. You'll see a lot done in 335, which is this dark blue here. You'll see a lot of that. You'll see a lot done in 193, and you'll see a lot done in 171, right here. Okay, and I have these labeled. So this is really the area, this is going to be our play zone now. We're no longer playing around with radio noise and those frequencies. We're playing now with frequencies of light that are in the ultraviolet part of the spectrum, because that lets us see what the physics, what the dynamics are going. And here is a ridiculously complicated plot that shows, well, not plot, but description that shows just the telescopes, the different measurements that the telescope, the SDO telescope makes in the AIA and the HMI. And it explains a little bit about that. And what's neat is that you can actually see. You see white light, but you also see helium-2, calcium-4, iron-9, iron-12. You'll see these emission lines come up again and again. They all are associated with a different wavelength or frequency of light, of ultraviolet light in this case. And so this is, again, a more detailed list of what the playground is that we are now going to be looking at when we look at flare dynamics. And I have plots of this stuff if you guys. You can also go to the SDO website, and they actually have, I don't know if it was Terry Kucera. I think I have her name on this last one. Oh, Karen Fox. So Karen Fox put this together. I think this is verbatim what she put. I may have simplified the language a little bit. I can't remember. But if you go to the SDO website, NASA website, you can see it. It's very easy to get really good explanations about this stuff. Okay, so let's talk about flare dynamics. What you're looking at in this case is on the top panel. You're looking, I believe, at X-ray. This is GOES. And so you're looking at a typical flare. This is not a huge flare. This flare wasn't even an M-class flare. This was a C8.8, I believe, back in 2010. But this was a paper that was done by Woods et al. And I think I'm standing over the citation. But it's a really good paper, and it's got a lot of good in-depth discussion of flare dynamics and how it works and how it compares to the model. So I'm using a lot of it this time. So when we look at the X-ray spectrum, this is a typical flare. You see it kind of go from GOES. You can see it kind of go up and then back down again. But in the middle of this, you see the stages labeled onset, impulsive phase. So onset is like precursor, is where we kind of see something happen and we know a flare is about to happen, and things begin to brighten, but it isn't explosive. It's just kind of slowly ramping up, and then it hits a trigger point, a kind of an instability where then things just go crazy. You know, it's kind of like a shopping cart rolling down a hill. It just begins to roll, and then once it just then really starts going fast. That's when we get to the impulsive phase. So the impulsive phase, as you can see, is very short. And then the gradual phase, we've got it in blue, lasts a bit longer. You can see time running down at the bottom. These are in, I believe, hours. So you can see the gradual phase, unlike the impulsive phase, the gradual phase will last hours. And this is oftentimes when amateur radio operators get a lot of their, their frustration, because you have a big solar flare and it just lasts and lasts and lasts, and it just doesn't go away because the radio burst is just not quieting down. Then you can have, and you can see overlaid here, something called coronal dimming. That's not necessarily a phase of the flare, but it's a good marker for those who are watching when the big solar storm erupts, the big CME erupts off. Coronal dimming is a way of seeing where the magnetic field was kind of torn off, where a lot of that solar storm left. I've often made figures that talk about coronal dimming. The dimming regions are always where you can see what part of the overlying field left along with that big coronal mass ejection that went out. And then you get the late phase. And you can see it really lasts. Okay, that's after the dimming for the most part. And the reason why is because now the CME is gone, and now those low-lying loops can refill. Remember I talked about chromospheric evaporation and how you get stuff that kind of comes, because it's been heated now by that flare. Now the stuff comes back up and fills up those tubes. And the tubes get bigger and bigger and bigger and rise a bit. That can happen for quite some time, as you can see, hours upon hours. And when you look at the bottom of this plot, the neat thing is that if we look at it in different wavelengths, let me scoot over a little bit, and I've labeled it now so you can see down here in the colors, here are the emission lines, and here are the wavelengths that you see it in SDO, in AIA. Okay, it's the same thing. But if you look at, so in other words, if you're looking at different images, different colors of the sun, if you go on the website, you can actually see a flare looks very different depending upon what wavelength you're looking at. So you can see in 131, you can see that impulsive phase really well. This is one of the reasons, that's that blue line goes straight up. Whoosh. That's why we oftentimes use 131 angstroms to look at flares, is because we can see that impulsive phase right away, and it happens very quickly. And you can also see it in 304. It rises pretty fast as well. 304 shows the chromosphere. That's often where you can see all the material of the big CME lifting off as well, is in 304. That's where you get those beautiful displays of junk just lifting off the sun. The blue sun is where you see mostly the light. And then, if you look at 335, that's the green line. it rises more slowly. It dips down. They all kind of dip down in the middle. If you notice after this dashed line that goes down, that's a lot where the coronal dimming happens. That's where the CME is lifting off. The material that is heated down at the base of the at the foot points, that ribbon has kind of died down, and now the evaporation is just beginning to happen. So it's kind of like a lull, right? Because the ribbons, the hot ribbons, the hot X-ray and all the impulsive stuff from 131 angstroms that you see, all of that stuff has begun to die down. The heating is now occurring, and now we're waiting for the evaporation for all that plasma to refill those flux tubes. Meanwhile, the CME has lifted off, and now all the dimming has occurred. So we get this kind of a dimming section or period of time. And then look back in the green. Now it begins to rise. Whoop. I don't know if I can do it right. See that? It begins to rise again. This is the late phase. This is after the CMA's left, the evaporation has occurred, and now we get these what we call post-eruptive arcades. And you see this incredible brightening. That's some of the prettiest things. And because you see these gorgeous loops and spindles. And it's one of the clearest indicators that a CME has erupted. It's also, if there is a way of trying to predict what a CME's orientation is going to be, the magnetic field orientation, this is one of the ways we do it. We look at the post-eruptive arcades because they straddle those ribbons. They're aligned along those ribbons, and they show which way the magnetic field is kind of pointing. If that slinky is going to be aligned along this way or aligned along this way, it shows us kind of what that slinky orientation is. And so we can say, okay, most likely the CME that lifted off looked like, that. So it's very interesting how we use this information. But I think I'll stand on this side. This plot that I'm kind of blocking right here, this is the one we just saw, right? These plots are other examples. And I've got, once again, the same emission lines, and I've got the legend over here, the AIA image that you refer to in the right colors. But look at the difference. This plot here, this is, what is it, a C2.0 flare. Okay? And you don't really see with this very weak flare, you don't really see a strong 131 angstrom impulsive phase. It's just not that intense, but it's only a C-class flare. It's a very low C-class flare. These are kind of the flares that we get now. So you're not going to get a lot of radio noise from them either, are you? Because you're not getting a lot of impulsive stuff. It's not a really strong thing, so you're not driving a lot of heating. You're not getting a lot of particles shooting down. You may get a CME from this, but it's going to be a much slower, much weaker CME. Here's one that is more of a actually, I think in this case we don't get any CMEs. That's why they're called confined flares. This next one, I think, that's an M. It's a bigger confined flare. This is an M-class flare, so now you get the impulsive phase. It's easy to see the impulsive phase. See that? But again, it doesn't last all that long. If you look at the amount of time, like the C-class flare, those are hours there. It's only lasting a couple hours. Here's another one that's not lasting all that long. Okay, you don't get a really long duration kind of thing happening because you're not getting a lot of post-eruptive arcades. You don't have a CME that's being driven off. There was nothing really in that top loop. You get something that breaks open, but nothing escapes the sun. And because of that, you're not getting a flare that's lasting. You're not getting all this other extra emission that comes out. You're not going to get big post-eruptive arcades that are then heating up and making it what we call a long duration flare because nothing erupted. And this is part of that solar flare myth. People used to believe back in the 90s that anytime you had a solar flare, that's where CMEs came from. And if you didn't have a solar flare, you didn't have a CME. And it took one of my colleagues, actually one of my advisors, Jack Gosling, the late Jack Gosling, to write a paper called The Solar Flare Myth to get people to kind of calm down and realize that's not how it works. Anyway, so then down here, here's one more. This is a long duration flare. This is a C3.2, looks like, yeah. See 3.2 long duration flare, and you can see how much longer it goes. Look how many hours now. Okay, these are the type that cause issues for amateur radio operators, especially when they're really powerful, because they'll have the radio bursts at high frequencies, but then they'll also have a longer duration issue and make those radio bursts last longer, because now you're driving a CME out. You get type 3, you get type 2. These emissions can last for a long period of time before things begin to quiet down. They weaken enough that they quiet down. And then here's a C4.4 long duration flare, and you can see it took a long time for that green down here, the green, to really heat up. But you see very slowly those eruptive loops, as they reformed, kind of bubbled up. The chromospheric evaporation was a lot slower. So again, a lot of different pictures here, and there's not one size fits all. And now I'll show you a kind of an example, hopefully to give you a better feel for what a solar flare feels like. In the top panel here, and I'll go into a cartoon after this, so that'll give you even more, hopefully even better feeling, because I know it's kind of hard to look at it from a line diagram and say, well, what does all this mean? So let me stand over here, because we're not really going to care so much about the HMI as we're going to care about the EUV. Okay, so what you're looking at in EUV, this is, what is this? This is 94 angstroms. So this is even hotter than 131 angstroms, so you're going to see a lot of impulsive stuff here. Then you go to 335, you're going to see a lot of the post-eruptive arcades, stuff that's happening more in the corona and the chromosphere. And then you're going to see here with, I think this is 171, yeah, this is 171 angstroms. This is where you're really going to see, this is my favorite, you're really going to see a lot of heating in those post-eruptive loops that occur. And then after this movie plays, I'll show you a diagram of this same event. So this is that, I believe this is that March, let's see, do I have it? Does it have it listed? Oh, come on. I'm trying to look at this. I think this is that March event. So let me go back here. This event here, or the May 5th. So it's this event here. So what's nice is that you'll see a nice clear, let me back up. Come on. You'll see, looking down at the bottom panel, you'll see the nice impulsive part. You'll see kind of a dimming a little bit, where things kind of quiet down, and then you'll see these post-eruptive arcades, where this green line goes up. If I can get my hand in the right place. Yeah, where that green line goes up. So it's almost like you're going to see 3 different stages. Okay? Okay. And one more thing I'll say is that this plot, oh yeah, I'll do this one here. This plot here, since I'm standing on this side, this is Eve at 335 nanometers. This is the 335 angstrom image, so it's the blue image that I'm blocking. And you'll see that peak, and then you'll see how the latter part of it rises slowly. Yeah, that's going to be the eruptive loops, and you'll see it even more in the 171. I wish they had plotted the 171 in this, but they did the 335. And then this other plot here, this is the Eve 9.4 nanometers, so 94 angstroms. That's the green image. So you're going to see a lot more impulsive stuff. You see that coming up early. So this one should brighten, and then these will brighten. Okay? And in fact, in both the 335 and in the 171, I'll see if I can point out where the dimming is. So where that lull is. So you get the impulsive phase, then you get this dimming, and then you get the long duration stuff. Okay? So see if I can play this and get the heck out of the way. See, if I'm going to stand here, right? Okay, so I'll try to back out that way. Okay, and play. Okay. Yahoo! So here it comes. Hopefully you can see the line. Now watching the green image, you'll see it light up really brightly, really fast. So you can see the precursor already happening, right? It's beginning to brighten. Wow, look at that. Boom! And then in 335, you see that X, that kind of weird X, that's the diffraction grating. Now you're seeing the dimming. In 171, you're seeing, see that dark in between the loop? That's the dark. Now watch, let me get my hand out of the way. Watch. Brighten, brighten, brighten. Watch the loops. Watch the loops. Come on, grow. Whoa, look at that. Isn't that pretty? That's the long duration stuff. That's from the chromospheric evaporation filling in those loops. So let me try that again. Okay, now that you know what to look for. Let me start it over. And back out. Okay, back out of the way. We'll do it again. And as that line moves vertically, or the vertical line moves across the plot, here comes the precursor looking green. Look at it go. And now, oh, impulsive. Boom, right there. That X is the diffraction grating. And now we're going into that lull. You can see the dimming, especially in 171, in between that loop, kind of right there, that dark spot. I can't point to it. There it is. And now we're going to get to that loops as the heating has already occurred, and now the chromospheric evaporation is happening, and all that material is moving back up into the loops. And that's how bright it gets. And that's the long duration part of the flare. But see, in green, you don't even see it. But you see it really well on 171. Look at those beautiful loops. And that can last for hours upon hours upon hours. As a matter of fact, there was one time I saw, and I'll just let that continue for a second. I think it's still going. Is it still going? Yeah, look how long this is lasting. There was one flare I saw that was on the limb of the sun. It was the east limb of the sun. And I have to go back. This was probably in 2015, maybe 2016. And it happened in the east limb, and it was amazing because, is it done? Yeah. It was amazing because when it happened, the flare, you couldn't even see the flare. It was kind of half occulted by the sun. But the loops were out far enough that you could actually see it over the horizon of the sun. And the loops, just after this huge, massive CME lifted off, and I think it went toward Mars or something. But I just watched it. It was insane. The loops went way high out in the corona and just stayed so bright. They themselves were like a C-class flare for something like 12 hours. And I just watched them burn and burn and burn. And I remember telling Nariaki about this, and I don't know if we ever got a chance to go back and look at it. But once that massive sunspot rotated into Earth view, it fired flare after flare after flare after flare after flare, all the way across the Earth-facing disk. Not one CME, not one coronal mass ejection, all impulsive flares. Because, and I know why, the thing evacuated everything on top of it. There was nothing left. The CME that left that went toward Mars was so massive, it probably took half the sun with it. And so when this thing rotated into Earth view, the sunspot itself was still incredibly unstable. But there was just nothing to evacuate. So it just kept lighting flare after flare after flare, but there was no CME to let go of because there just really wasn't anything worthwhile above it. And I've never seen anything like that since. But, you know, I've only been doing this, staring really at the sun since I became the space weather woman. I didn't watch real-time events like this or do a lot of heavy solar physics prior to. So I'm not as skilled as people who do this, you know, who focus on solar effects. But that's always an event I've always wanted to go back and take a much closer look at, and maybe someday I will when I'm teaching these courses, and use it as a really good example of the solar flare myth. As a matter of fact, maybe by next month I'll see if I can go back and find that particular event and show you movies of it, because it's just spectacular, and it really is a good example to show that you can have really strong impulsive flares and no CME be lifted off that follows. And the flares look very different because they don't have all this late phase stuff going on. So it's very interesting. Anyway, so let me at least show you this diagram. So this is a nice diagram that was put together. Again, you can go to the NASA Goddard website to get this. As a matter of fact, this is an article that Tony Phillips put together ages ago, and one of the scientists, and I apologize, I don't have her name on here, she had put this together using some of Wood's, the stuff from Wood's paper. And if I stand on this side, so we can talk about this, you can see this is that same event, and now we're looking at, this is just kind of a cartoon, overlay of the 171 angstroms image, because it showed, that was the yellow sun that showed all of the really pretty loops coming up. And then the middle panel is that same image without all the cartoony stuff on top of it. And then down at the bottom is a difference image that really shows how the loops stand out. So if we walk through the timeline of it, so it walks from basically left to right in the timeline, you can see the pre-flare configuration. This was before the flare. You can see how the loops were closed, and you had this, the small loops down at the bottom. These are the loops that become the ribbons underneath them. And you can see the drawing of it that she put up on there, and then you can see just the AIA image. They say 17.1 nanometers, it's 171 angstroms, same thing. And then the difference image you can kind of see, it's a little bit messy down at the bottom, but you can see all the smaller loops. So up here is the model that we're kind of looking at, and then here are the observations that kind of bear it out. Now once you get to basically she goes to the main phase of the flare, that's meaning more like the impulsive phase. You're having this flare erupt, you're having, whoops, yeah, okay. I want to make sure I'm pointing to the right place because I'm looking at the TV over here and it's late. Yeah, you're having the flare erupt, and that's when it got really bright in the green images, right? And this overlying loop begins to pull out and reconnect and get the magic is happening, and you're going to get a CME that comes out here. And you can see down in the 171 angstroms, that's why you're seeing that really bright region right here. Whoops. Come on, hand. Go to the right place. Right there, that small loop underneath, that's where all that's happening. And you can see down in the difference images, you can actually see where the dimming is beginning to occur. So down here at the bottom, and you're seeing the direction of that CME, which way it's going to be lifting out. Now when you get to the transitional period, this is kind of that lull. This is where the dimming has basically occurred, everything, and especially in 171 angstroms, you can see the dimming now, not with difference images so much, but with in the actual raw images themselves. The CME has lifted off, and you haven't quite rebuilt anything yet. All the heating has occurred, and you're just beginning to get the chromospheric evaporation. It's not really happening yet, but the CME is lifted off. You now are getting dimming. You can see that dark cavity. If I go right here, there's the dark cavity. Come on, right there, yeah. There's the dark cavity, and that's showing the dimming where the CME is actually torn off the sun. The main part of the flare, the impulsive part, has died down, so now we kind of get to a lull, and that's that transitional period. And you can see in the difference images, you can see some of the loops, and the dark parts of the loops now these are loops that are I think beginning to reform, and what is literally left over. Then when you get to the late phase, let me step over here. Now you're getting those outer loops beginning to reform. That's what she's trying to show with this fuzzy blue structure here. In 171 angstroms, of course, the spindles look so much better. I mean, you can just see literally all these tiny little flux tubes. It's like the little spirals of the slinky, right? You see all of these little tiny little spindles, and they're all being filled with this hot plasma that's been heated from the impulsive phase of the flare and all the material being shot down. Now it's beginning to rise back up. It's creating what we call the post-eruptive arcades, and you can really see them very brightly in the difference images as well. And then the post-flare configuration. Once everything kind of calms down, this is after, at the very end, this is after the flares happened, after the chromospheric evaporation's kind of settled down, everything's kind of come back to more or less, I want to say more or less an equilibrium state. But the post-flare configuration oftentimes look very much like the pre-flare. So there's not much difference between the post-flare and pre-flare. And the funny thing is, if the region that's caused all this is unstable, then that gives you an idea between the pre-flare and the post-flare looking very similar. That gives you an idea as to why flares can keep happening from the same region over and over again. It reconfigures and changes things, but it doesn't change it so much that there's no chance of a flare ever happening again. If that sunspot continues to grow, more flux emerges at the foot points down at the surface, and it begins to twist things up and cause more instability, then this process repeats itself over and over and over again. And that's why when we get these really big bad actors on the sun, they will spew a flare and again and pow, 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 all the way across the disk until they've disappeared on the other side. And that takes 2 weeks, right? From east limb all the way to West Limb. That can take 2 weeks, and we could get slammed by, geez, what did region 2673 do? 25 flares in 10 days. Not even that, 7 days, I think. And this sunspot, when it came up, this was the one that killed us during Irma and Harvey and Irma during Anne Marie during 2017, back in September. This sunspot didn't even show up on the east limb. It emerged about 2/3. Well, I want to say 2/3, about halfway to central meridian. If I'm looking at the Earth-Sun line, it emerged right here, about halfway to it. So we only had, about 10 days of this thing at all. And within 7 days, it had shot 25 M-class flares and I think 4 X-class flares, and gave us like 2 or 3 solar storms, radiation storms, gave us the whole works. I mean, it was insane. So this is why those bad actors can keep doing it, is because the pre-flare configuration and the post-flare configuration really aren't all that different. And so it really can set it up for yet another flare. So, okay. Wow, a live show. Love unscripted events like this. Thank you. You're welcome. How long will this KP7 last? I don't think we're at KP7. I came here looking for an answer and was attacked by this so-called specialist. Uh-oh. Oh, well. Yeah, Frank is a strong-willed person, but he's very protective. So hopefully everybody can play nice. Anyway, I will take anybody have any questions right at the moment? I mean, I can go back and take a moment to take a break. We're getting really close to the end, but I want to be able to, get opinions or get questions if there are any. What cools the sun? That's a really strange question. I don't think radiation. It radiates out, and basically the solar wind pulling off of the sun. All of that is adiabatic cooling. So it's the sun is cooling just simply by emanating its own solar wind. So I guess that hopefully that answers that question. Why does the polarity of Earth's magnetic field flip, and why on such an irregular basis? That is a very complicated question. It has to do with the Earth's dynamo, and a magnetic dynamo, and it's not really a subject for this course. I do talk about it in one of my prior courses, I think about indices. I actually talk a little bit about the Earth's magnetic dynamo. I will later on do another course on the Earth's dynamo. But don't worry about the pole flip. It's going to be probably a lot of fun. Not nearly as much of an issue as you might think it might be. Let's see, what is the most impressive thing we do with plasma? I don't know. I think the most impressive thing we do is have fluorescent light bulbs. I mean, we have plasma in a lot of light bulbs that we use on a daily basis. Neon beer signs are great too. Plasma's all around us all the time when we use it pretty constantly. Let's see. Do we know the approximate speed of the wavefront produced by the CME pulse? You mean on the sun? When a flare happens, oftentimes you can see the EIT, you can see waves going across the solar surface. That's a blast wave that happens. I've talked about that before, I think, in sunspots and telescopes. So there's that blast wave, and yes, they can measure the speed. We also measure the speed of shock waves out in front of the CME and the CME itself. That obviously depends upon the CME, how explosive, how eruptive is it, how much power is there. And so it varies. It can vary anywhere. We've seen shock waves that travel 3,000 kilometers a second. We've seen CMEs that travel nearly 2,000 kilometers a second. That's on the fast side. We've also seen CMEs that are moving so slowly, they're actually being lifted and surfing the solar wind because they're so slow, the solar wind is slamming behind them and pushing them out. So, it's a whole zoo. What happens to the sun as many meteors and asteroids hit it? Don't they mix up with the sun's coronal atmosphere? They probably don't make it. They might make it hit the solar atmosphere, but the solar atmosphere is constantly blowing out, so they just get blown back out with the solar wind. Really, they burn up long before they ever come close to hitting the sun. And every time you see sun-diving comets and then someone says, oh, look, a CME happened because of the sun-diving comet. Seriously doubt that. The sun hardly is so large, and its fields the configuration of these fields are so massive and so global that it wouldn't even notice that. it'd be like, you know, less than a mosquito bite kind of thing, hardly even noticeable. So I don't think that you're going to see you know, unlike a planet where you can actually see a comet like Shoemaker-Levy causing, you know, issues with Jupiter. You know, the sun is so much larger and its fields are so much more tenuous. Really hard to say that there's anything effective causing something like a coronal mass ejection launch, just due to a comet. If it even notices it. Okay. Any other questions thus far? What effect did that event with Mars have on the planet that we know of? I believe that might have been one of the ones where Curiosity rover had to be turned off because there was a huge radiation storm associated with that event. And I have to go back and look, but I do believe that was one of the ones where because at that time they had already realized that they needed to turn Curiosity rover off because the radiation storms that Curiosity was experiencing were pretty intense, far more intense than they ever expected to get. I think the biggest one that they saw two really huge ones. One was in 2012, and then of course the one in 2017. That was that near Carrington class event that occurred from region 2673. As it was leaving we were watching it disappear around the Earth's west limb, or the sun's west limb. It launched a huge coronal mass ejection along with an X8 class flare, 8.2 or 8.3 class flare, and I'll talk about that. I'll probably talk about that next course. And it launched the biggest radiation storm that Curiosity rover had seen with its radiation detector. So yes, there are definite impacts when they get to Mars because the radiation storms actually make it all the way to the surface because the atmosphere is very tenuous there, which tells you something about, you know, having human colonization on Mars. Just getting there is half the battle. Surviving being there is maybe even a bigger challenge. But I've already used the word cavalier so many times, I'm not going to talk about it anymore. Okay, so let me get back to this. So let me just mention, I'll get on this side, why are solar flares classified using X-rays? And here's an example. You guys see me put this chart up pretty much you know, every week when I do my solar forecasts. This is obviously during a period of time where the sun was a lot more active than it is now. And it goes X-ray flux, and you see two different versions. You see high, more like two different forms of soft X-rays. I don't think it's using hard X-rays here. But the X-ray detector, two different wavelengths or frequencies, whichever you want to call it, is showing X-class flares and M-class flares. Anything that goes up above the X-class line, you see, you know, like these two big red peaks. And then there's a few others that look like they're M-class flares. I'm kind of blocking one. If I stand back a little bit more, you'll see there's an M-class flare right here, there. And a lot of C-class flares below that. But the reason why we end up using, with all this stuff, we have EUV, we have radio waves, we have all sorts of ways of registering or observing a solar flare. Why do we use X-rays? And the reason for that is because the soft X-rays in particular have such a huge dynamic range, meaning they go really, really quiet and they get really, really, you know, intense during solar flares. And so it gives us this massive scale on which we can measure stuff. And as a matter of fact, this scale, for those who don't know, this scale is logarithmic. So it's like a Richter scale. So it's going up, you know, by a power of 10 every class. It's not a linear scale. So it allows us to really have very sensitive measurements of solar flares. So we can measure the really, really tiny ones and the really, really strong ones with one instrument. And that's why we've used X-rays to classify flares. No other instrument will allow us to do it without getting totally saturated. But obviously, this is not the whole story. So when amateur radio operators or anybody looks at X-ray flux data and tries to understand what the solar flare is doing, you're just looking at one aspect of the observation. The X-rays may have died off already, and you're still experiencing problems. Well, why is that? You know, the X-ray flux says the flare's over. Yes, but the EUV long duration part of it is not over, and so you're still experiencing issues. So just keep that in mind when you look at X-ray flux. And then, of course, we can even get to white light. Believe it or not, some flares are so intense you can get to white light. So you actually see it not just in the ultraviolet, but clear down into the white light wavelengths. And here is an example of a white light flare back on July July of 2002. So what you're going to see is white light on one side and then 170 nanometers at 1700 angstroms on the other side. So here we go. Let's see if I can get out of the way. Oh boy, get out of the way. Is it playing? I don't know if it's playing. I think it stopped. Hold on. Please play. Oh, hopefully can I make it keep going? Oh, I may not be able to make it keep going. Shoot, it goes so fast. I thought I had this on loop, but maybe I don't. Let me duck down so you can see it. Come on, play. So you can see on the left side, you can see the white light part of it. But you're not going to, whoops, come on, don't do that to me. You can see on the white light, it doesn't last all that long. You can see part of the ribbons, but you can't really see the whole thing. Oh, why is it? I have no idea why it's doing that. It's not letting me play it twice. There we go. And we do it again. Can you see all that? So you can see in ultraviolet, it lasts a lot longer. But just to be able to even see it in white light is a feat. That means that this particular flare is so powerful and so strong that you could actually see it all the way at Earth from the ground. Because white light, if you've seen some of my other courses, you know we have an atmospheric window, and extreme ultraviolet doesn't penetrate all the way to the ground because our atmosphere absorbs it. But white light you can actually see on the ground, of course. And so what that means is that with a solar telescope on the ground, you can actually look up and see the ribbons of the flares occurring. But it does mean that it's an incredibly powerful flare. And believe it or not, that's exactly what the Carrington flare was. This is why Richard Carrington, way back when, and another gentleman who also witnessed the same flare, were able to draw it. They were able to, back on September in 1859, am I pointing the right way? Here we go. This is the image that he drew, and you can actually see the ribbons, right? He actually drew the white ribbons. It's a 2-ribbon flare. That was a really ugly sunspot, very, very, as you can tell, very, very unstable. And this is down here, this is a plot of what the magnetometers did down here at Earth once the big CME arrived. It went completely off scale. Something that was supposed to be on the top scale here actually dropped clear down to the bottom and overwrote what was on the other scale because it was so massive. But this one was believed to be pretty much the largest flare that we've seen since then, since the dawn of modern telescopes. And I'll just mention, let me go over here for a second. I will go over this in more detail because some of this stuff was associated with the flare and some of this stuff was associated with the actual CME that hit later. And this is part of the reason why so many people get confused when they talk about space weather and they talk about solar flares and coronal mass ejections, is because the same event essentially hits you twice. First, the solar flare causes problems right away for you, and then a few days, or in this case only like 17 hours later, the CME hits and it causes more problems. So people have a tendency to think that solar flares and CMEs are the same thing. And maybe they are associated. We've seen that they're associated. They don't always have to be a one-to-one association. But this is why the public gets confused, because they have very intense impacts at Earth, and they don't happen simultaneously, but they happen close enough in time that people oftentimes think that they're the same thing. So I'll go over this more when uh-oh. That's weird. Okay. That was weird. I'll just do this. I'll go over that more when I do the actual events. Okay, and we're getting really close to the end here. I had gotten a question from one of my Patreon members about TSI and about solar flares when it comes to TSI. And let me stand on this side. And they said, you know, with solar flares, why don't you see the total solar flux index go up? Because they're so bright, why don't you see that? And the trick for that really is that it's not really happening in white light very often. Only the very big flares go up in, actually have emissions in that area, in that wavelength. So here's an example of what we typically see with solar flux index during, let's say, big flares. You actually, unfortunately, see the flux index go down. See this drop? That's typically because there's a big sunspot on the disk, and that sunspot is visibly dark. Remember how we talked about it early on? This is, as a matter of fact, that same example that I showed in one of the earlier slides, where it showed the TSI dropping like 0.34%. That's exactly what this is. It was because of a big sunspot group that actually darkened a significant fraction of the sun that it was measurable in TSI. But let me tell you, there is a component where it goes up. If we take this part and we blow it up, okay, and we go, so I'm going to stand on this side of the screen. And now this top panel, you're actually looking at that drop. Okay, it's kind of spread out in time a little bit, but you're looking at that drop. Okay, that's that 0.34% decrease. But you notice it's kind of irregular, right? Those are because there are normal solar variations that happen all the time. But believe it or not, it is possible to subtract that out. Not until recently were we able to do that, but we have been able to do that. And when we do that, in this particular case, there was a strong flare. If I can point to it, it was an X17 flare, I believe, X17 class flare, that occurred. And you see this little tiny lip right there that we're pointing at, that tiny lip? Well, if we blow that up to the bottom panel here, this is what we see. And this red line that shows this jump, that's the effect of the solar flare, because it's all in the EUV wavelengths. It's not so much in what we would consider, not the massive part of the total solar flux index. It's just a very small section. And we actually know that it correlated with the actual flare, because when we actually look at the X-ray flux data, and I believe that's X-ray flux data, isn't it? Yeah, it goes. So that's the X-ray flux data, and they actually have down here the first derivative, which actually shows the ramping up. The first derivative is an acceleration. So it basically shows how fast something is brightening. And the intensity of the total solar flux with that little jump that you see in red, that jumps up more, it's a little bit more aligned with the acceleration with this first derivative than it is with the actual intensity of the GOES flux. But it does show us that the TSI is sensitive to solar flares. So when people say, well, TSI isn't sensitive to solar flares, and why isn't it? Well, it is. It is sensitive to solar flares. But typically, the solar flux index goes down when there's solar flares, because of the big sunspot group that's driving these solar flares ends up darkening the visible spectrum of the sun. And this is kind of what I wanted to show here. Let me stand on this side. So here is, if I can stand far enough away, here is a plot in wavelength down at the bottom. You can see going from small wavelength all the way up to longer wavelength. And then intensity, so basically irradiance is intensity, the brightness. Everything that has been put in the red bracket, that is the extreme, the XUV, EUV, and FUV. That's where flares dominate. Look how low the intensity is, right? Compared to where we get into the visible range, look how much more intense. Okay, total solar flux is down here. This radiance, this UV, the UV irradiance really, on average, doesn't even count for, what do I have on the top bullet? 0.007% of the total solar irradiance, typically. And when flares occur, okay, it increases quite a bit. But still, as you can see from the prior example, the total solar irradiance will typically drop because of a solar sunspot, because of a sunspot group that's driving it. And so you don't notice the contribution from the solar flare nearly as much as you'd think. And that's why when you look at TSI and you look at GOES X-ray and you're like, well, what's going on here? Why can't I reconcile the two? It has everything to do with wavelength and what wavelengths you're looking at and what wavelengths matter. Now, that's for total solar irradiance. However, let me stand on this side. And this is the second to last, this is basically the last informational chart for this course. Here's something I want you to, it's going to kind of set up the next class, and I want you to keep this in mind, because even though you don't really see flares in terms of the total solar irradiance, you see it in the X-ray flux, and okay, yeah, it does what it does, and you see it in radio bursts. Believe it or not, the ionosphere is actually very sensitive to the EUV contribution. And when you look at, in this case, GRACE, this is daytime density. This is neutral density at about 500 kilometers in altitude here at Earth. Okay, and this was back in 2003 when we had a really big, one of the big X-class flares. This was that X17 flare that you saw, that I showed you in the total solar irradiance just a moment ago. Had only the tiny little lip as far as a contribution, right? This is what it did to the Earth's atmosphere. What happens when sunlight, especially ultraviolet light, impinges on the upper atmosphere, it can either increase or decrease the density, the neutral density of particles, of the constituents in the atmosphere, depending upon what the constituents are and what altitude. In this case, we're talking about an increase in density, in neutral density. And look at this. You've got the black line, I think, shows GOES data. Let me see if it does. Yeah, X-ray flux. So that black line shows the impulsive X-ray event. And look, right after the impulsive event, look how much the density increased at GRACE. Okay, so this is in the Earth's upper atmosphere. This is due to solar flare, due to the EUV component. This isn't due to a radio burst. This is due to EUV component. This is not the sun screaming. This is the sun shining, okay, during a solar flare. And we get these things. They're called sudden ionospheric disturbances, SIDs. And these types of disruptions, which can last for hours, as you can see in this plot, and depending upon the kind of flare, now that you've seen the dynamics of the flares, with those long duration events, with those post-eruptive arcades and the chromospheric evaporation filling those loops, right? Kind of, the hot plasma evaporating back and filling those flux tubes and causing all that heat and more emission, more EUV emission. That emission then can cause these SIDs to last and change and die and, reform and all this, all this kind of stuff. And this is where you start having issues with radio propagation just from EUV. So these these sudden ionospheric disturbances cause single frequency deviations. They actually call it in ionospheric physics, they call it SFDs. I don't, okay, fine. I don't work in that field enough to know. But they definitely affect GPS and GNSS. They can affect radio propagation, signal propagation, along with the radio bursts, and obviously are a dayside phenomena, and they can actually be enhanced if you're near the dawn dust terminators, because things are changing quite a bit already. And anytime you get fast changes like this in the ionosphere, you're going to have problems with signal disruption. You're going to get problems with signal bending and refracting and all sorts of other things, because you're getting a lot of conductivity changes. You up the neutral density in the atmosphere, you change the conductivity of it, and it suddenly becomes a layer. And so something that was a single layer, suddenly if you increase the neutral density at that altitude, suddenly you get two layers. You get a layer that wasn't there just a second ago. And now anything that's bound, any signal that's trying to hit it is either going to be bent as it goes through it, or it's going to bounce off it. Or it's going to scatter, like twinkle, twinkle, little star, just scatters, scintillates. And these are the types of things that we don't understand all that well yet in ionospheric physics, especially when it comes to signal propagation for GPS and GNSS. These are the types of things that we're just beginning to get databases big enough that we can start really sampling and understanding it and realizing how big of a problem these things are. Because, you look at total solar irradiance and there's no problem, right? Not a big deal. It's not necessarily true. Okay, so we're getting there. We haven't done everything yet. We've gone through flare dynamics now, and gradual versus impulsive, the main phase, long duration flares. We've now gone through kind of the neat phenomenology, both from the radio frequencies and the radio communication side of it, as well as the pretty UV visible solar imagery side, and kind of putting that model together and that picture together of flare dynamics to know not only what's happening on the sun's surface and how things are being shot both up and down, but also what it looks like, and then as it propagates out to Earth, what is going to be affected. Okay? We still have yet to talk more about the solar flare myth, which I've talked a little bit about already, and then how hydro flares fit into this picture. Also, maybe even that event that I mentioned was a really cool event about evacuation of material, and maybe there's just nothing left to erupt. So you can get a lot of impulsive flares that are very powerful, but there's just nothing shooting out towards Earth. And then, of course, I've yet to talk about all the big events that are associated with this stuff, how we get the huge disruptions, not just from the radio bursts, but also from EUV. And I won't talk about the big solar storm stuff, because that's CME. We already talked about that. But as you can tell, there are disruptions that occur just from either the solar flare or the radio bursts associated with it. Doesn't even require a CME. So hopefully this we're setting the stage for further discussion. And yes, I know I still need to get into the planetary radio emission. We've got charts on that too, but that was going to have to wait till next time as well, because I've talked more than 2 hours, so I'm sure you guys are sick of me. So let me take a look and see if you guys have questions. I'm not going to answer questions about gamma rays right now or gravity right now. Can we talk about stuff that has to do with radio bursts and solar flares? Flare dynamics. Okay, I watch these effects daily on 50 megahertz. Yes, I know. I'm trying to slide back a little bit to see what other questions we might have. Please just simply Google solar storms, heart health effects. Yes, it can truly affect people. Just look. No, Rachel, I agree with you. It can affect. The problems that we have, however, is that there are a lot of medical, pseudo-medical research studies that have been done where, as I start reading through it, and they associate things with storms and solar this and solar that, they get everything wrong. And so they start making correlations that really aren't physical. And that's kind of what I'm trying to do when I create this database. I've got one of my VIPs helping me create this database, and we are sifting through material that is either pseudoscience or just stuff that their approach is wrong, their assumptions are wrong. And we say, okay, well, that we can't really keep. We got to push that aside. And then the stuff that looks like it's actually got something to do with it. Like there's actually some really interesting studies about solar cycle and longevity, people's lifetimes. People who were born, and I never knew this, but people who were born during solar minimum live longer than people who were born at solar maximum. Did you know that? Is that total trip? Trips me out. Like, I was born at solar maximum, so it looks like I'm going to die really soon. No, but nonetheless, it's a very interesting set of research, and it looks to be reasonable from a physics point of view. But then you come across other stuff that it's really kind of crazy, and some of the things that they assert about solar phenomena are just so off the wall and wrong that that any conclusion they come to from that point out is going to be irrelevant and probably wrong. So that's what we're trying to do, is kind of weed out the riffraff and read out, get the stuff that could actually help somebody if they were trying to understand maybe some personal issues that they've had. So yes, we are working on that, and it's going to be a long time before all of this comes to be mainstream science. But I think the first thing to do is get it into the fringe science realm. Perk up everybody in fringe science and say, hey guys, some of you who actually know what space weather is, can you look into this? And hopefully that will begin to raise the number of people that are working on that. So then mainstream science begins to take a look. And that's how you transition. You transition things from being a complete crazy idea to fringe science, where you get some reputable work done. And then the mainstream science can't help but look at it, because it's like, well, wait a minute, this is pretty reputable. We got to we really need to, let's make some instruments, let's write some proposals, let's get some real government funding to be able to do some really deep dives in this that fringe science can't really do, because they don't have the wherewithal and the training to have done it, and they don't necessarily have the credibility or the clout. So that's how you migrate. That's how we all work together, and so I'm hoping that we'll get there. But it will probably take decades yet for that to happen. But we're getting there. Okay, so Dr. Tamitha looks cute struggling versus the machine. Oh, that must have been when I was doing the flare thing. Yeah, boy, it was a pain in the butt. Okay. Oh, good. I'm so glad you guys are learning more stuff. That's great. Dr. Scove, does the alignment of Venus, Earth, and Jupiter have anything to do with the sun's 11-year cycle? Tidal forces. This is the same problem I have when it comes to earthquakes. We know tidal forces play roles, right? I mean, the oceans move, right? We have tides that come in and out. So tidal forces, of course, gravity plays a role in everything. Could it play a role in the sun? Well, sure, right? The problem is it's not just 11 years, because the solar cycle goes from 9 years to 14 years and back again. So is it that simple? No. And the paper that's out talks about it being like clockwork, and it's silly. Plus, you can go reference papers that were done 100 years ago, rigorously, from scientists that already thought of these very basic questions. Don't you think that if there was a rigorous thing, at least in mainstream science, and a very easy solution and a very, very convincing one, that mainstream science would have adopted it by now? It isn't that convincing, because there's a lot of other things that are saying, well, that's not really a strong enough force to play a huge role. There's all these other things going on. And it's the same thing that we have with earthquakes. There is a primary cause of the sun's dynamo. There is a primary cause of Earth's geological motion and earthquakes. And those primary causes have not been sussed out very well yet. The models that we have that could capture what those primary causes are and subtract them out of the equation don't work very well. And until we can get those models working well, we can't subtract out those primary effects to get to the lower level effects, which are things like tidal forces, right? It's the funny thing to me is that everybody talks about, for example, with earthquakes on Earth, everybody talks about how the sun is affecting those earthquakes, and sun is and Jupiter and Mars and all these planetary alignments. And it's like, well, what about the moon? The moon has by far the strongest tidal influence on Earth that there is, and yet we still can't find a really tight and ironclad connection between the lunar tidal forces and earthquake activity. And if we can't even do that, why would we dream that we could do it with the sun and these other planets that are so much further away and have so much of a weaker influence on Earth? So do I think the effects are there? Sure. Do I think that we have any chance of quantifying what those effects are yet? No, not a chance. And this is why mainstream science steers away from those questions. There's lower lying fruit for them, lower hanging fruit that they need to get and solve before they can tackle these much harder problems. And sometimes I think the Fringe Science Society thinks that that means we're poo-pooing it, that it doesn't exist. No, we're not. We just can't answer the question, Give us a chance to try to solve the easier problems first before these harder problems become the main things that we go after. I mean, I won't even get into it, but it's the same thing with the sun and the tidal forces. It's the same problem that we have with space weather and earthquakes, is that the science just isn't there yet. And so yes, could there be correlations? Sure, why not? We just don't have a ghost of a chance of quantifying them. And I'm not sure when that time will be, especially when it comes to the sun and the solar dynamo. Solar dynamo is really complicated. We do think that there are, the team at UCAR and NCAR are doing an amazing job, because they're looking at so many other things other than sunspots. They're looking at, obviously the underlying magnetic field, but they're looking at coronal holes. They're looking at how filaments migrate, what we call rush to the poles. They're looking at bright points, not just plages, but the small bright points, and the butterfly diagrams that are associated with them. They're looking at all sorts of things that most scientists don't look at when they look at the solar cycle. Most scientists just look at the sunspots. But these people are this team is actually trying to configure the whole thing and get the big picture. And I think they're much closer to finding the truth when it comes to how the solar dynamo works than probably any other team. But they're almost considered fringe. sadly, by the mainstream scientists who have these old theories that they don't want to let go of. For obvious reasons. There's lots of good stuff in those theories. So when a new mainstream science team challenges the old ideas, it's hard to get it adopted. So, for instance, my good colleague, Dr. Scott McIntosh, he's been fighting the good fight for a long time, for years and years, to try to get some of his papers accepted, and they don't want to. You know, there's people who have had have kept him out of certain journals for a year and a half, working on some of these papers, simply because they don't want to change their ways. So anytime people in the fringe science, by the way, fringe science community think that mainstream science doesn't have the same problems, that we're all one big happy family, you're completely wrong. We do the same thing in mainstream science. There are people who have new theories, and it's really hard to get the new theories into the fold and accepted. And fringe science is just another chapter of that. So this is why it kind of boggles the mind to me that people fight so much between mainstream and fringe, because we're really all one family. And we got to help each other and stop fighting each other. It's kind of crazy. Anyway, I hope that's a long-winded answer to your question, but hopefully that answered something. No, I don't have a past video speaking on health effects. Yeah, I know. Everybody's very interested in it, and I can't do one yet because I don't honestly have enough information. Let us try to get this database going, and then I might do a course that's just about going through the database, because I will not diagnose, I will not try to treat. The only thing, because I am not a medical professional, the only thing I can do is set the stage for hopefully medical professionals to step in and start doing more rigorous work. That's the best I can do. But I can help arm people with information, that there is information out there, and we got to start doing more digging. But that will be probably the extent of any course I do on health effects with space weather. Let's see, okay. Can you elaborate a bit on the effects of a flare in the near-Earth space environment? Didn't I do that? The flare itself wasn't, that it just happens on the sun, but it's a coronal mass ejection that comes out, and all of the radio burst and stuff that comes out that affects Earth. And I had that one plot. As a matter of fact, I'll go back to it. So if you came into the class late, here is, goodness, there it is. Go back to this chart and a few of them before it. And this talks about how the coronal mass ejection that is now shot into space, what we also call an ICME, interplanetary coronal mass ejection, makes it all the way out to Earth and causes all the issues once it hits Earth, and all the low kilometric radiation that happens once it's inside the Earth's magnetic shield. So hopefully you can catch that. What do the dot values mean? I missed that. Okay. Anyway, I'm going to go back down to see if anybody has some new comments, and then I'll check Patreon. Let's see. We are not seeing how these energies affect human consciousness. I don't think anybody knows this yet. Okay, what? Isn't that where the scientific method should rule? If it's reproducible, shouldn't that be convincing to the mainstream? Oh, right. Sure, in an ideal world, but you think scientists don't have egos? You don't think scientists have empires that they've built on a particular theory and philosophy, and that if they're wrong, their entire empire crumbles? Come on. They're still human, and they still have mouths to feed, and money to make, and proposals to write, and grants to get, and reputations to protect. So they're just like anybody else out there. I mean, the funny thing is I work in music and I work in science, and I remember looking at the two and seeing the squabbles and the egos, and I'm like, geez, this scientist over here has lead singer's disease, and this scientist over here has lead guitarist disease, and and it's like everybody wants their fader higher in the mix. And it's exactly the same way in the scientific world too, is that everybody wants to hear their voice the loudest. And so it was amazing to me when I realized how similar the two crowds were, because it just let me know that humans are humans, and it doesn't matter what field you're in. So anybody who's a shoe salesman, the people that you deal with day in and day out aren't going to be much different than the attitudes you deal with in science. I hate to say it. So, I mistakenly got into science because I thought that maybe people were going to be seeking the truth more and be more honest when it comes to, and more open-minded when it comes to new ideas, and that the truth would be the one, torch that they'd hold out above everything. And it's just not true. And it's not necessarily because people are evil. None of the scientists are evil. They just honestly have those biases towards their own material, right? They've got to be the best. I mean, how else do you think they got to where they are? And so it's just the same thing that you see anywhere else in the world, in any other profession. And just apply what you already know about life and about people to the scientific community. And it's amazing how unromantically, how unromantic an answer that is, but it is absolutely the truth. So yes, we struggle even in mainstream science to get new theories and things adopted. It's not an easy task. Look at Parker, Eugene Parker, right? When he put the whole model out for the solar wind, you can go find, because of Parker Solar Probe, you'll find a whole historical perspective on it. He was ridiculed for decades for his model, and he almost didn't get it published. And this is just the way it is in science, Fringe becomes mainstream, but only typically after decades of fighting. And of course, the theory has to be sound, because only a sound theory will withstand decades of fighting. So it's, there's checks and balances. Anyway, it's almost like politics nowadays. Okay, some scientists are evil, like the brain and Pinky. Oh, geez, you guys are funny. Okay, yes, funding and tenure is a political process, unfortunately. Exactly, it really is. And it's become even more politicized, and that's part of the reason why I wanted to start this field, was because if we can get space weather into a broadcast medium, and it becomes more something that is part of our everyday weather, then a lot of this funding fighting, a lot of this infighting because the funding is limited, because the field is so obscure, some of that goes away. Because now it becomes part of weather. More people want to do it, granted, but also there's more money to do it with. And that, I think, is really going to be the big normalizing factor when it comes to space weather, is if we can pull it into terrestrial weather, we're going to solve a lot of problems. We may create a few more, but we're going to solve a lot of them. And also we're going to do a huge, there's going to be a huge benefit to society, especially as we become more spacefaring. Because like I said, I've used the word cavalier far too many times today. And I use it pretty much every time I teach a course, because there's so many examples of where we are being cavalier in our race to space, and now our new race to the moon and to Mars. And we're not paying attention to the details. And the devil is always in the details. So, okay. King of the mountain principle, yes. The irony, truth is in people as scientists with biases, yeah, it trumps truth, yes. It's just the way it is for human nature. Religion more so. Well, science becomes religion, right? Depending upon how you define the religion, scientists, they have their own religions. So, okay, what is your opinion of Dr. Zarkova? Right. Well, she's, the nice thing is that we're all going to know within the next year if solar cycle 25 comes on time, Zarkova is going to be, wrong. And I personally, I think Zarkova is wrong, and I think solar cycle 25 is coming. We've already seen evidence of it, so I do believe it's coming, and I do believe that that the methodologies are used is limiting, and is not considering everything. But I, as a scientist, I have my reasons for saying that, and I'm not gonna say that Zarkova is not a reputable scientist just simply because there's a difference of opinion here. That's the one thing that good scientists do not smear other scientists simply because they disagree. It's completely logical and normal and healthy for scientists to disagree. But the nice thing is that the truth always wins, and so whatever the sun's going to do, it's going to do, and we'll know very soon, probably easily within the next year. So I don't think we're going to our grand solar minimum. Our grand solar minimum phase, we're already in. But that only means that the solar cycles get smaller. Doesn't mean they go away completely. And so it's a modulation of the solar cycles that are already happening. But as we know, it's the asymmetry of the northern and southern hemispheres that cause the problem magnetically. And so when they're out of phase like they are now, that's a grand solar minimum. But the problem is with that comes a more complicated magnetic field on the sun. And what comes with that are more things like Carrington class events, because you get a more complicated magnetic field, you get more unstable sunspot groups coming up, because you're getting hemispheric band compression and all these weird things that are going on that make the sunspots more like bad actors. So just in this last solar cycle, we've had two, if not three, Carrington class events. Only one grazed Earth. And I'll talk about that in the next, well, no, I won't. I talked about that in my CME course, the last of my CME courses. I talked about it. This was the CME that was shot away from Earth. It was actually shot like this. The sun was pointing this way. It was shot out that way, and the bullet that came from the gun, if you can look at it that way, was so big, it actually grazed Earth, if you're Earth. I mean, this thing was massive. This thing was also the one that caused the largest radiation storm on Mars. So, you know, Carrington class events can occur with small cycles, and there is evidence that they occur more often with these low activity cycles than with the big activity cycles. So even if being in a grand minimum doesn't guarantee that you're safe from big events. As a matter of fact, it may be the opposite. And it also causes problems because now we're being bombarded by cosmic rays a lot more than we ever used to. And we're having to deal with that aspect, especially with airlines. And now if we're going to go to Mars, this is the worst time to go to Mars. The cosmic ray impingement is 30%, if not higher, than what it's ever been during what we call the grand maximum period. So this is the worst time to go to Mars, even if it is a shorter shot, you know, because of the planetary alignment. The thing that you have to understand about space weather is that there is no good time for space weather. When the sun quiets down, cosmic rays get worse, and the big extreme events get worse. When the sun gets more active, cosmic rays quiet down because the sun shields us from them. But there's more activity, so there's more events happening. You know, it's just, there's always something hazardous in space weather. So hopefully that answered that question. Okay, can you suggest good learning material? Not at this level. Everything is either for children or it's for graduate level. And so that's why I'm doing these courses. And that's why we're starting this Millersville graduate certificate. Unfortunately, you'd have to become a Millersville student to do this, and it's going to be aimed mainly at either practitioners in meteorology or students of meteorology who want to become space weather broadcasters. So that's the certificate program we're creating, and that's what some of these training materials are. But you can obviously go and take a look at the courses I've already done, and that will help because they're all at about this level. As Earth goes through a pole shift and the magnetic field diminishes, how much more susceptible are we to CMEs and cosmic radiation? Oh, well, again, a bit more, then that goes beyond this course. I promise I will do a course on that. But I'm not going to do that until after I get through radiation storms and the rest of these solar flares. And then I'll talk about probably coronal holes, and then I'll get into Earth and some of the issues with the Earth dynamo. But let me check really fast. I'm going to get off this for a second, and well, let me do it over here. I'm going to check my Patreon feed to see if there's anyone who's asked questions on Patreon. Let's see, anybody ask any questions? Oh, okay. I don't think I have any more. The only other question I had from Patreon is going to be one that is relative to the space weather recently. An amateur radio operator was asking me if I understood why there was so much noise on the bands recently. To be honest, the best I have for you is the fact that radio propagation is so bad right now because the solar flux is so low that even the minor disturbances that we are getting with the slow solar wind or the fast solar wind that's coming, it's not that fast. Once it gets up to unsettled conditions, once we get up to even about 450 to 500 kilometers a second, radio propagation is so unstable on Earth's day side because it's so low, it's so bad, that these minor disturbances can cause a much larger disruption than it should, and you get more noise on the bands because of that. But there's nothing going on in terms of radio noise right now. The X-ray flux is way down. It's a spotless sun. We just don't have a lot of radio noise. So the fact that the noise floor is really high right now, or it has been over multiple bands, I think has a lot more to do with the fact that we've got issues with the solar flux being low. And that's the best answer I can give you. Outside of that, I don't know. So anyway, okay, so any other questions? Let's see. It looks like I pretty much got it, guys. Yeah, we're going to have to, yeah, I'll have to, how can the cycle, I will answer this. How small can the cycles get? Can they vanish? Yes, and that's exactly what the Maunder minimum was. Let me take a sip here. And some of the other ones, the Sporer minimum, which was even deeper than the Maunder. What happens is that the cycles don't really vanish, but they vanish visibly. Because what happens is that in order for, and I talked about this in sunspots and telescopes, and I believe I talked about this during the last radio burst course, because I talked a lot about sunspots. And what happens is that in order for a sunspot to appear, to emerge, and I oftentimes call them submarines as they pop above the surface and then back down, what you're looking at is a magnetic flux tube, okay? And it's a magnetic tube that is displacing what is essentially boiling plasma. So think of it like a boiling pot of water. And if the boiling pot of water is the way the light from inside the sun reaches the surface is through the boiling, the boiling water, then if you displace that water, then suddenly you don't get the light anymore. And that submarine, that magnetic submarine in a sense, as it pops up through the surface, is displacing all that boiling water. So now the light is gone in the area where that submarine is. And that's why it's dark. But in order for the magnetic submarine to rise up and pop through the surface, there has to be a certain amount of magnetic buoyancy. In order for that to happen, there has to be a certain magnetic field strength. When the cycles diminish so much that the magnetic field strength of these submarines goes below, I don't know, it's like 2,500 Gauss or something, some number, I forget what it is. But once they get below a certain amount, they can't penetrate. They can't pop through the surface. So sunspots don't appear. They stay below, they stay subsurface. So it's basically all the submarines stay below the surface. And therefore you don't really see submarines. And you don't get as much magnetic field or as much activity. There are still activity cycles. There are still filaments, there are still eruptions, there are still things, but you're not getting nearly as much solar flare activity and that type of thing because there's no sunspots coming up. And that continues until the modulation, the grand solar minimum, so to speak, modulation releases enough so that the magnetic field strength of the sun can build back up again. And it's most likely due to this asymmetric hemisphere issue. You've got a magnetic north and a magnetic south, and if they're not aligned, then they can cancel each other. They can work against one another, and they can weaken the sun's field overall. And I won't go into the details of why, but that's what they do when they're out of phase. Kind of like, constructive and destructive interference when it comes to waves. So it's the same kind of idea. In this case, it's magnetic field strength. So when it weakens enough, if they're out of phase enough that they really destructively interfere with one another, it weakens the overall magnetic field strength of the sun and therefore weakens the strength of the magnetic submarines that are popping through the surface and creating sunspots. And so we end up getting a spotless sun for, maybe a cycle, maybe more than a cycle. In the case of the Maunder minimum, I think it was something like 76 years. The cycle still continued, you just didn't see them. There were no sunspots to really count. So it looks like the cycles stop. But the convection still happens, the flip still happens, all of that I believe still happens. It's just that we don't have the sunspots necessarily to monitor to show us that it happens. And then suddenly, at some point, the cycles seem to start magically all over again. Yeah, probably because they never stopped. They just got really dim. Hopefully that answers that question. Okay, I think that's it, guys. And let's see if there's any other questions. The 4 magnetic fields are now supposedly 180 degrees out of phase. I have no idea what that... 4 magnetic fields of what? Can you recommend some books for those comfortable with math and physics? At what level, Scott? Yes, Baumeihound and Troyman. It depends upon what subjects you want. Ruby, Chris Russell's book. He was my thesis advisor. He did, it's Russell and Kivelson gosh, space plasma physics or something. I can't remember the name of the book anymore. We call it Ruby for short, R-U-B-E-Y. But it's Chris Russell, C.T. Russell, R-U-S-S-E-L-L, and Kivelson, Margaret Kivelson, K-I-V-E-L-S-O-N. And it's a graduate, first-year graduate level fundamentals of, not space weather, but space physics in general. So it goes all the way from the sun all the way to Earth, and it gives you a really nice overview. Has math, definitely has math. If you're comfortable with electromagnetism, you know, undergraduate level E&M courses, maybe math methods for physics. If you're comfortable with those levels, obviously calculus based, yes, that's an excellent book. It doesn't go too deeply into the details. If you want something even higher level, Bamihan and Troyman have a really good book out. There's a couple others I could recommend, but boy, the physics gets pretty intense. And then the only thing I would say is, if you don't want to get too in depth in it, don't go into things like wave mechanisms and dispersion relations and things like that, because that's when things really get into the weeds. Any of the stuff that has to do with kinetics, physics, kinetic processes, and you get away from E&M and you get more into the collisional and kinetics of things, then you can get into trouble. But if you stay with magnetohydrodynamics and some of the simpler aspects of it, the math isn't too bad. So hopefully that helps you. Okay. Discord chat. I don't have a Discord. You know, I haven't had anybody ask me about Discord yet. I have no idea how to set it up. So Chrome Air, you know, yeah, I'd love to, but it's just me running the show, and I don't have a team or anything. It's just me. All this is just me. So I haven't been able to get to that point yet. Why was a solar observatory shut down? What, that one a while back? I don't even remember anymore. It had nothing to do with aliens, so don't worry about it. Okay. Scaremongering GSM news videos. Oh boy. Okay. Yeah. You know, the GSM thing is all over the place, and some scientists have been associated with that, and it's unfortunate. Some reputable scientists jumped on it early on. Then this is back, oh my gosh, almost a decade ago. They started talking about the grand solar minimum, and we were going into another Maunder, and you know, fire and brimstone. And I just remember getting so frustrated because it was so early to tell what was going on, and I think there's been a lot of leftover. I think at the time social media was just ramping up, and scientists didn't realize how much their PhD weighed on the media, and so they would say things that they would say in a scientific arena because, you know, that's what we do. We discourse, we talk about it, we, you know, put stuff out there and then let it get eaten alive, and if it survives, it survives. But when you do it with the media, oh man, they pick up and run with it, and it's fact. Before it's even out of our mouths, it's fact. And so I think a lot of us early on jumped on this GSM bandwagon, and without even realizing that, you know, we needed to be more rigorous with our observations. And then, you know, like helioseismology, they started seeing evidence of the next cycle, and a lot of the science went, oop, mea culpa, and backed off. And yet the media is, you know, they're already 3 miles down the road saying the sky is falling, and you know, and you just can't take that stuff back. So I think that's kind of set it up, and this was more than a decade ago. So we just have to kind of deal with it. Hopefully we'll be a little bit smarter. Hey, from Denmark. Hi, good to see you. Okay, sorry. All right, guys, it looks like I think we've caught up on basically all the questions that I will be able to answer out of this. And as far as the Earth's magnetic field, I promise I will get to doing an Earth's magnetic field dynamo thing for everyone, and talk about how cool it's going to be when the poles flip, and how we could actually have aurora in Hawaii and Brazil as opposed to Alaska and Iceland. And you know, we'll have it at mid-latitudes, and it might be really, really fun. Of course, it's going to make flying via GPS nasty, and everybody who has a compass is going to get, you know, have to throw their old compass out the window and get a new one. But it's going to be, it'll be a very intriguing time, and I don't think our generation's going to see it, but a few generations down the road definitely will, and things are going to be very different. And what's really freaky, and I'll go into this because this will be all speculation, it'll be a fun part of the course, I'll talk about how the Earth's radiation belts are going to shift, right? I don't think I'll be crazy enough to draw a picture of it, but my goodness, even as scientists haven't really talked about how the Earth's radiation belts are going to be, how they're going to be affected and what shape they're going to take when the Earth's field flips, because the Earth's field, when it flips, I mean, it looks terrible. It's just stochastic craziness. So we may not have radiation belts for a while. There just may be crazy, intense radiation all throughout geospace. And that's going to wreak havoc with all of the satellites that are up. We're probably going to have to design them completely differently, because right now we design them according to what orbit they fill. You know, a LEO bird is a lot different than a GEO bird. There's way different radiation environments, way different space weather issues that they have to deal with. And so that's all going to change. So it's going to be a very interesting time. So yes, I'll do a course on that and talk about some of the effects that nobody else is thinking about. Because these are the real world things that we are going to have to deal with. So, okay. I think that's it, guys. And it's been great, and I hope you enjoyed it. And, you know, leave me more comments below. And if you have more class ideas, please join me on Patreon. Patreon is where I end up getting all my ideas for classes and what to do next. And I thank everybody who is a patron of mine for joining me and for helping make this class possible. Okay? Thanks a lot, guys. I'll talk to you soon.